Right. I hope you believe with me that that was a wonderful, still is a wonderful meeting. Anybody knows who is to thank for this wonderful meeting?
Not you.
Not me. So Megan and Alicia are truly responsible for doing everything.
All right, so the first talk of this afternoon session is given by Liang. And so Liang will tell us about the universal bounds related to the gap and how what's the mathematical response.
Yeah, I'd like to first thank the organizers for putting together this wonderful event.
You did right.
Okay.
Shines in eyes.
Yeah. So and also for having me here. Yeah, great pleasure. So I'm going to talk about some recent theoretical work that is perhaps a little bit different from other talks you've heard so far, but we will see there are also connections with other talks. So I'm going to discuss basically insulating states that have an energy gap, and I want to ask a question: what can we learn about the energy gap from knowledge of the ground state? For example, the topological invariant of the ground state, and the response of the ground state at the DC. So thermodynamic response. So this work is done in collaboration with my brilliant student. How do I turn the page? Yeah, Hugo Onishi, who is here in the audience.
Sure.
Right. So this slide sort of summarizes the question we are asked. So we know that there are, broadly speaking, two types of quantum phases. The gap states. In this case, there's a finite energy gap between the ground states and the first exact states. Thank you. And in the an example is integers. And another class of quantum phases are gapless states and such as metals. So the question is, what can we learn about the energy gap from knowledge of the ground state? So let me first review a little bit what is known in the literature. There's a general consensus, right, that if you have a finite energy gap in the spectrum, finite spectral gap, this is intimately related with the exponential decay of correlation function at large distance. And the correlation function is a property of the ground state. So for example, if you look at the spin system, look at the two-point spin-spin correlation, if it decays exponentially at a large distance, and this Cassie defines a correlation length, then we know that if your spin system has some emergent Lorentz invariance, for example, you're dealing with one-dimension spin systems, then this correlation length is naturally related to an energy scale, which is an energy gap through a velocity. And in this case, a finite correlation length then also implies a finite energy gap. So there's a lower bound to the spectral gap. And more generally, for lattice systems that do not have Lorentz invariance, there's a very profound mathematical physics study by Hastings and others. This is really beyond me, but they show that if you have a non-vanishing spectral gap, that implies exponential decay of correlation length at large distance for quite general class of boson and fermion systems with short-range interactions. So I'm actually going to talk more about another kind of a bound, which is an upper bound. And famous result from Feynman and BJ is that we can actually provide an upper bound to the energy excitation energy of a system, again through the correlation function. Here, S of k is the equal time density correlation function is a ground state property, and the delta K is the gap between the ground state and the first excited state at a given wave vector K. Okay, so so this formula is derived on the very general conditions for neutral systems in a quantum fluid state. For example, in the case of the boson superfluid, we know that the energy excitation energy spectrum looks something like this. At a small momentum, you have a linear branch, which is just the photons. But then at a finite wave vector, there is a dip in the excitation energy. This defines a Roton minimum. And one can actually get a very good, using this inequality, one can actually get a very good bound on the Roton energy by just measuring the ground state correlation function experimentally. Okay, it's a famous result. And then in the 1980s, this approach has been applied to quantum Hall states, and in particular, fractional quantum Hall states within a lambda level. Famous result by Gervin, McDonald, and Passman. And they actually applied the Feynman BJ formula, but with a novel twist. Okay, we know that fractional quantum Hall states arise from interactions in the partially filled lambda level. So this many-body energy spectrum, in a sense, all come from interactions within the lambda level. And when the interaction is weak compared to the lambda level gap, h bar omega c, it makes sense to restrict the Hilbert space to just the lambda level itself. And in this case, one can define the so-called project density correlations. So this n bar is a density operator projected within the lambda level. And this actually gives you a very good bound to upper bound to the excitation energy in fractional quantum Hall states. And in particular, this whole branch is called the magneto-Roton mode. And one can calculate the energy spectrum by, for example, excitation. And one can also use this formula to look at the right-hand side, the bound. And the bound is only obtained, requires only the knowledge of the ground state wave function, for example, the Laughlin ground state wave function. And they also work very well. The bound is quite tight. So these are pretty much the, as far as I know, the important works about the bounds on the energy gap. Okay, and you can see that these two examples, superfluids in quantum Hall states, are somewhat specialized. A very, very important subject, but somewhat specialized. But I'm going to talk about the gap in a much broader setting. Okay, so I want to remind you that the energy gap is very important for many purposes, in condensed matter physics. For example, if we talk about electronic insulators, simple band insulators, and in this case, the energy gap determines the color of absorbed and emitted light. And this is how an LED works. Right? If you want an LED with different colors, you have to choose materials with different band gaps. And we also know that insulating states can be topologically non-trivial. Example, in addition to quantum Hall states, quantum spin Hall states, but also three-dimensional topological insulators. And in these materials, the bulk energy gap is very large. It can be on the order of 150 millectron volt. And in the bulk of the energy, inside this bulk energy gap, there are these gapless surface states which survives up to room temperature. So in general, for topological states, having a large gap is desirable because we want topological quantized phenomena to survive at high temperature. But large gap is desirable for high temperature topological protection. So one question we can ask, which to my knowledge has not really been thought about before, is that is there an upper bound on topological gap? Okay, for a topological insulator, is there an upper bound? Can it have arbitrary large gap, or is there an upper bound? So this brings me to the results of our work, and the results are just summarized here. Okay, so the two pieces of work, one is work from summer last year. We showed that there's a universal upper bound on the energy gap that is purely based on the topological quantum number of the ground state. And in particular, we are thinking about two-dimensional systems with a quantized Hall conductance. And this Hall conductance in units of E squared over H defines a many-body Chen number. It's known through the TKN formula. And this many-body Chen number can be either integer or fractional. Okay, so then we find a bound that for quantum Hall states for Chen insulators, integer or fractional, the energy gap has to cannot exceed this quantity, which is basically n over mc. N is the electron density, m is the mass, and c is just the Chen number, or quantized sigma xy.
This is a band mass, or this is?
I'll come to that. Yeah, I'll come to that. Yeah. Okay, so this bound, the right-hand side is purely based on topological invariant, so we call it topological bound. And then earlier this year, we derived another relation between the energy gap and the thermodynamic response of the system, in particular the dielectric constant epsilon, the static dielectric constant. And this formula that is shown here is basically, h bar times ne squared over m epsilon naught is just the plasma frequency for electron gas at the density n. So the numerator is basically h bar times plasma frequency. The denominator is the square root of dielectric constant minus 1. Okay, so these are the results. These are exact results that are generally applicable to any insulating states. So now the rest of the talk is basically I'm going to show how these results are derived, and we're going to apply it to several cases. Yeah, so you will see this soon. Yes. Okay. Okay. So the way we're going to derive these bounds is very, very simple. We're going to think about optical response of an influence. So we're going to shine lights, okay, and look at optical conductivity. And so yeah, this quantity is a spectral gap. Again, to remind you, defined as the energy between the ground states and the first excited states. So these two bounds are all derived in a very unified way by considering this quantity, which we call generalized optical weights. And in the general, it's defined as follows. It's the real part of the longitudinal conductivity plus I times the imaginary part of the Hall conductivity divided by omega to the nth power, and then integrate over all frequencies to infinity. So the real part of the sigma xx and the imaginary part of sigma xy are dissipative parts of the optical response. Okay, and to make our life simpler, I'm going to first look at the thermodynamic bound, which does not even involve the Hall conductivity. So to simplify things further, let me first consider just this quantity is defined by the real part of sigma xx. So this, what it is basically is a negative nth moment of the optical conductivity, the real part of optical conductivity, right? So for example, if you look at n equals 0, this is nothing but just the optical spectral wave. Okay. Now, what can we say about this? The real part of the longitudinal conductivity has to be non-negative at all frequencies. This is because the energy dissipation must be positive. And also, if the system has an energy gap, then the real part of sigma xx has to be 0 for a whole range of frequencies, from 0 until Eg divided by h bar, and where Eg is the defines an optical gap. Okay, so the optical gap has to be at least as large as the spectral gap, because optical transition is only possible when I connect the ground state with some excited states in the spectrum. But in many cases, the optical gap can even be larger than the spectral gap. A simple example, if you have a bending insulator with an indirect gap, optical transition is at Q equals 0, so the spectral gap can be small, but the optical gap can be large, right? But what I'm going to do is going to derive an upper bound on the optical gap, and therefore this bound is also an upper bound on the spectral gap delta. Okay, so the rest of the talk I'm going to focus on the optical gap. So once we have this quantity, then and just using these two properties, we immediately can see that we can have a whole series inequalities, because in this integrand, if I replace the denominator omega by the smallest frequency at which optical absorption is possible, in other words, replace omega in the denominator by Eg, then we're going to obtain an upper bound to this optical weights. So that's why, for example, W0 is greater than Eg times W1, which is greater than Eg squared times W2. That's why our energy gap appears in this inequality. And then this immediately leads to a whole series of upper bounds on energy gap. We can, for example, combine, take the ratio of W0 and W1, that give you one bound, upper bound, or you can take the ratio between W1 and W2, that's give you another bound, or you can be more creative, take the ratio between W0 and W2 and then take the square root. Okay, it's actually easy to see that these bounds all satisfy this whole series of inequalities. So basically, the more power of omega you put in the denominator, this quantity, optical spectral weight, is more and more sensitive to optical absorption at low frequency. So that's why there's a series of these bonds. And all these bonds are saturated if and only if optical absorption occurs at a single frequency. Okay, single frequency. Okay. Oh, sorry. Yes. Slides. Okay, so now we're going to look at this formula more, and in particular, as we just said, W0 is a full optical spectral weight, and if I think about the F sum rule, what we learned from F sum rule since Kubo, this optical spectral weight is actually a ground state property. It can be written as the second derivative of the Hamiltonian with respect to vector potential that evaluate over the ground state. And interestingly, for Hamiltonians with kinetic energy that's p squared over 2m, then this formula becomes very simple. It's just n squared over m. This is basically the full spectral weight. And here, n is the full electron density, including core electrons, and m is the free electron mass. Okay, so let's back to Superior's question. And to remind you, this F sum rule is completely general. It actually just follows from instantaneous response. Okay, that when you integrate over all frequency, that's equivalent to look at the response of the system to a pulse of electric field, and the pulse of electric field basically accelerates all the electrons and give it some finite momentum, finite current, and that's how the F sum rule basically is about.
So what about core electrons?
Core all included because it's an instantaneous response. So all those electrons respond instantaneously to the applied electric field. Now, in order to get a bound, not only I need to know W0, but also we need other parts, right? So in particular, let me look at this bound shown in the middle, which involves the ratio of W0 and W2. So what is W2? Now, actually, it's simple to see. W2 is actually directly related to the static dielectric constant. So let me remind you that conductivity is just the ratio of the current and the applied electric field, but the current is a time derivative polarization, and therefore conductivity is directly related to the polarizability, the response of the system to the polarization in response to the applied electric field. And the polarizability is also related to the dielectric constant, basic dielectric constant -1. Okay, and then so if I look at the W2, which have 2 powers of omega in the denominator, I express the real part of sigma in terms of imaginary part of this polarizability chi. I get this relation here, right? Now, then we can use the Kramer-Kronig relation. Kramer-Kronig relation relates the imaginary part of chi divided by omega to the real part of chi evaluated at 0 frequency. And this is basically the thermodynamic polarizability, which is equal to the static dielectric constant -1. Okay, so basically through the Kramer-Kronig relation, we can see that W2, even though it's expressed in terms of the full frequency integral, is also a ground state property, or to be more precise, it's a thermodynamic response. Now we can
if the material is strongly anisotropic,
yeah,
it feels like you'll have a lot of different chi's, but only one gap. So which one are you going to use?
So we can apply this to chi, all the diagonal components, chi xx, chi yy, chi zz. They give you different bounds, but whatever is the smallest.
Okay.
Yeah, whatever is smallest. Good question. Okay, so now combining these two pieces of information, W0 and W2, we can now derive upper bound on energy gap, which is what I said earlier, the plasma frequency divided by the square root of epsilon -1. Okay, so here plasma frequency is just defined as n squared over m, which is the plasma frequency for electron gas at density n. Okay, and also note that in the whole discussion, I'm applying this formalism to a system of electrons. We assume that the nucleus is at fixed positions. So this the epsilon dielectric constant here is really the electronic component of the dielectric constant. So no electron phonon effect yet. Okay.
And so you don't allow any delta function conductivity.
So we're dealing with insulators.
Yeah.
Yeah. So the sigma of omega is actually 0 at frequencies below the gap, the real part of sigma. So there's no singularity at 0 frequency.
So I'm so confused. I mean, so if I count in n, if I count all the core electrons, say of copper, all the way down to 1s.
Yeah,
Yeah,
absolutely.
it's going to be a big number, right?
Let's look at next slide. Next
So-
slide. Next slide. Next slide. Excellent question. Excellent. So we look into all kinds of materials, insulators, right? Not copper because that's a metal. So all kinds of large gap, small gap insulators. And my student Hugo did a great job collecting this information. So based on the chemical formula, based on lattice constant, you can easily get the electron density or electron density. And the M is a free mass. So this is an energy gap, optical gap, measured from optical experiment. And then through this, this is the electric constant, epsilon. And the electronic component of the electric constant in literature are denoted as epsilon at infinity. This infinity just means the frequency is much higher than the phonon frequency. And we can then look at our bound, which is denoted as EG maximum. And then you can look at the ratio of the observed gap, optically measured gap, and the bound. And for many materials, the bound is actually pretty good, right? For example, look at silicon, very important, technologically important material. It actually the real gap in silicon reaches about 45% of the bound, and the absolute winner is a cubic boron nitride. In this case, the gap reaches 72% of the bound. So we can plot all these information in this graph. Y-axis is the energy gap measured from experiments. X-axis is this density divided by epsilon minus 1. So in this log-log plot, the theoretical bound will show up as a straight line, and you can see that indeed, right, all these materials fall below this bound. And some of the materials, especially the ionic large gap insulators with light chemical elements, these are actually very close to the bound. On the other hand, if you look at topological insulators, narrow gap systems, heavy elements, these are pretty far from the bounds. Okay. Now we have this result, and then we were very happy. We wrote it up, and it turns out this is only half the story. Later, we realized, when we apply this result to a three-dimensional system with long-range Coulomb interaction, there's actually a very interesting subtlety. Okay, so if you have a 3D charge system with long-range Coulomb interaction, there are really two types of long wavelength excitations, and these couple to longitudinal and transverse electric field respectively, and they have different excitation energies. Okay, it took us a long time to appreciate this. And a simple example is that if I have a three-dimensional electron gas in a periodic potential with Coulomb interaction, we can imagine that the interaction is so strong that the electron form basically a Wigner crystal that is pinged by the periodic potential. And in this case, the low energy Hamiltonian of the system are just basically phonons of the system. And the phonon Hamiltonian can be written in this way. The first term is just the kinetic energy associated with lattice with vibrations, electron vibrations around the equilibrium position. The second term is quadratic in the displacement field. It's very similar to what Leo wrote down yesterday, but because we are dealing with a charge system, there's a very important, the coefficient is not just a constant, unlike in elasticity theory, but it's Q alpha Q beta divided by Q squared. And this just comes from the fact that the divergence of displacement is related to the charge density. Okay, and then the last term is because of pinning by the external periodic potential. So there's omega 0 squared U squared term. Now you take this Hamiltonian, immediately you realize that if you take the Q goes to 0 limit, you have to be very careful. If you look at the longitudinal vibrations, when the vector U is parallel to Q, in that case, the energy gap is the square root of omega p squared plus omega 0 squared. Omega p is a plasma frequency. But if you look at the transverse mode, in that case, the gap is just omega 0. So there are really two different types of excitations and different gaps. So what kind of a bound are we talking about? Now, correspondingly, we can actually derive two types of bounds. Okay, there's one gap bound for longitudinal excitations and another bound for transverse excitations. And in the interest of time, I'm not going to go through all this, but this is something I really enjoyed understanding, going through the old literature. It turns out that all this Kubo formula we learned in textbooks, right? There's a difference between the Kubo conductivity defined by Kubo formula versus the physical conductivity. Okay, because the Kubo conductivity is defined in response to applied electric field, while the physical conductivity is defined in respect to the total electric field. Okay, so when you are looking at the transverse response, they are the same in the Q go to 0 limit. But if you look at the longitudinal response, they're different. The difference is exactly the dielectric constant. And also, so this is why the sigma T and sigma L here are the cubical conductivity, and they are related to the physical conductivity or the physical dielectric constant in different ways. And there are two primary sum rules that we found in here. Okay, and so there are two Kramer-Kronig relations. One is for epsilon minus 1, the other is for 1 minus 1 over epsilon. And we benefit enormously from this early paper by Water-Kong and others. But then, tracking through the literature, in the end, we found that there's a beautiful discussion in Landau and Lifshitz. Okay, the Landau-Lifshitz actually is very interesting. So most of the early literature, like Pines and Nozier, they discussed this second sum rule. 1 over epsilon satisfies the Kramer-Kronig relation because 1 over epsilon is related to the density correlation function. Okay, but interestingly, so that's why we have no doubt about the second one. But the question is about the first one, right? So we found it by thinking about the cubical conductivity and shown here. But then, we found this interesting discussion in Landau and Lifshitz in this volume on electrodynamics. Landau and Lifshitz devoted several pages to discuss actually a Kramer-Kronig relation for epsilon. And then at the end of this discussion, there's also a paragraph saying that, by the way, it also applies to 1 over epsilon. Okay, so I still haven't quite digested, but I find this fascinating. So the punchline is that there are two kinds of sum rules in the Coulomb system in 3 dimensions, and correspondingly, there are 2 types of gaps. So the gap that I showed you earlier is for transverse excitations. And this indeed is the gap measured by optics because electromagnetic waves are transverse. On the other hand, if you are interested in longitudinal excitations, then there's a different gap bound. It's h bar omega divided by square root of 1 minus epsilon inverse. Sorry, there should be a square root here. Basically replacing epsilon minus 1 to 1 minus epsilon naught. Okay, so this implies that if you have material, it has a very large dielectric constant near some, for example, ferroelectric distortion, when epsilon blows up, this means that the transverse gap actually must be very small, must go to 0. But on the other hand, the longitudinal gap can still remain finite. So, yeah, yes?
This is a very strange question. So in the Coulomb system at Q equal to 0, you're talking about essentially about the depolarizing field, whatever it's called, which depends on the sample shape.
It doesn't. So we can always think about finite Q for infinite system, and then take the limit.
It's not 0 Q. It's
let's just about finite Q. Right. Yeah, and take the limit Q go to 0. Yeah. So we can try more. Yeah. And what really we are convinced because of this example. Think about the because I'm talking about gap bound, which is the intrinsic property of the system in the absence of any perturbation, right? So the gap in the energy spectrum is a well-defined quantity, and if you look at this example of Coulomb gas in the periodic potential with strong interaction will form a Wigner crystal, and you can easily see that there are 2 different kinds of excitations, and they have different gaps.
So this DQ is D2Q or D3Q?
D2, no, D3, D3Q, 3D,
okay.
3D.
Yes, 3D, okay.
Crucial,
okay.
That's crucial, 3D.
That's crucial, yes. So that's the question, basically.
3D.
Yeah. All right.
Yes.
Just return to the screen, please.
Sorry.
No, return to the screen.
Okay. It took me a long time to understand this. Okay. Yeah. Okay, good. All right. So now let me move on to yes.
So what's the relation with the actual spectral gap that you see in?
Oh, that's the optical gap. So that's the transverse gap. So all the stuff I showed you earlier is all correct. All correct.
And the longitudinal. So
how do you probe it? That's a different question. I don't know the answer. Yeah. So one thing I'm very curious is have experiments really check these sum rules for dielectric constant and its inverse. To my knowledge, I don't know any tests of this experimental tests. So it'll be interesting. Yes, question.
So if I were giving the ability to diagonalize the Hamiltonian exactly and get the many-body gap, which gap should I compare with?
So there are 2 kinds of gaps because so what is a gap, right? Gap is defined as the energy ground state and some excited states. You can look at the excited states that couple to longitudinal electric field that defines the longitudinal gap, or you can look at the excited states that couples to transverse electric field that defines the transverse gap. So there are really 2 different types of gaps.
Talking about the gap in a system with a fixed number of particles. You don't add particles, right?
Fixed number of particles. Yeah. In spectral gap. Spectral gap. Yeah. Thanks. Yeah. Okay. So now let me move on to the second part of the talk. The second part of the talk, is about two-dimensional states with a quantized Hall conductance. These are quantum Hall states or chain filters, integer or fractional, doesn't matter. So really, what I call by C is just synonymous to sigma xy in units of e² of h, and the result is shown here. Again, very simple. N over m divided by C. Okay, how is this obtained? Okay, so let me again now let me look at the energy gap bound defined by W0 and W1. Right, W0 is just the full spectral weight, and W1 is this quantity, the real part of sigma xs divided by omega. So it turns out this quantity is actually related to many interesting things. It's related to quantum metric, first pointed out by a very pioneering work of Eva Soda and Wilkins and Martin. It's in the non-interacting systems. This quantity W1 is related to the spread of the binary function. In disordered systems, related to the localization length. And recently, we showed that in the general case, in two-dimensional systems, this W1 is related actually to just the static structure factor in the small q limit. But you don't need to know any of this. Okay, you don't need to know any of this. So all I want to say for the purpose of deriving a bound, that we see that the energy gap has to be bounded by the ratio of W0 and W1. If we can get a lower bound for W1, we will be able to derive an upper bound for the energy gap. So the question is, how do we provide a lower bound for this quantity W1? And since we are dealing with quantum Hall systems, and we should look at both longitudinal and transverse Hall connectivity. So sigma xx is time reversal even, sigma xy is time reversal odd. So let me now come back to the full definition of the optical spectral weight we defined a year ago. It now has it's now a complex quantity. The real part is the real part of sigma xx. The imaginary part is the imaginary part of sigma xy divided by omega integrated over all frequencies. So now let me give you a very simple result that the real part of W1, which is the quantity that's important for us, is actually lower bounded by a quarter times the Chen number. Okay, and again, this result is obtained in a very general way. Okay, from here. So what we need to do is let's consider circularly polarized light, either left or right-handedness. And in this case, the absorbed power J dot E, which is the real part of sigma xx plus minus imaginary part of sigma xy times E squared. Okay, and the second piece corresponds to so-called magnetic dichroism. If you have a time reversal breaking material, the absorption of left and right circular polarized light is different. Okay, that shows up at the second term. Now we know that the energy absorption has to be non-negative. This then immediately implies the real part of sigma xx must be bounded by the absolute value of imaginary part sigma xy, and this has to hold at all frequencies. Then we obtain that the following inequality, the quantum this negative first moment of sigma xx is then lower bounded by the negative first moment of imaginary part of sigma xy. Okay, and again, I'm going to use pharmacronic to rewrite this term as the sigma xy, the real part of sigma xy at DC, and that by definition is the Chen number. This is just a DC quantized Hall conductance, right? So this immediately gives me the result. So you see, this derivation is entirely based on just the positive energy dissipation and the pharmacronic relation for optical response, and the pharmacronic relation is purely based on causality, the fact that the system cannot respond before you apply a perturbation. Okay, and therefore this result holds very generally for any gap systems, interacting, non-interacting, chain insulator or fractional chain insulator, all works. So combining these two, we just get this result I showed you earlier. And again, this bound is on the optical gap, which generally can be bigger than spectral gap. So if I have just 1 minute, then let's look at two examples. We can look at this. So okay, first, again, back to the question, what is N and M? So this bound obviously works for Hamiltonians of microscopic Hamiltonians of all solids, right? Because all solid state Hamiltonian has a kinetic energy that's p squared over 2m. And in that case, then N is a full electron density, M is a free electron mass. In this case, then the right-hand side is enormously large, 10,000 kelvins, not so useful. It's still fundamentally important that there actually is a bound on the gap of quantum Hall states, but the bound is so large, it's not actually useful. But then we can actually apply this same reasoning, same derivation to effective Hamiltonians. Okay, for example, if I have a semiconductor in the electron in gas in the magnetic field, in this case, we know we describe the kinetic energy as p squared over 2m, where m is effective mass. And I have a external magnetic field. This gives me a quantum Hall states. And in this case, then the bound actually is exactly equal to h bar omega c. Okay, because the n is proportional to the filling factor. The Chen number, the sigma xy, is also proportional to the filling factor. The ratio is just h bar omega c. Does this make sense? Well, this is we know that for example, there in the integer quantum Hall states, non-interacting systems, the spectral gap is exactly h bar omega c. So the bound is saturated. Even more generally, if I have interactions, we have fractional quantum Hall states, the spectral gap is very small, because much smaller than h bar omega c, but optical gap is exactly h bar omega c. And this is because Kohn theorem says optical absorption can only occur at this frequency, omega c, and it only works for circuit polarized light of one-handedness. That's exactly the condition for saturating all these bounds. So this also means that our bound for general case, for general chain inhibitors, is as tight as possible. It cannot be further improved. So let's now look at just one last example. The quantum Hall states without Landau levels. These are the chain inhibitors, fractional chain inhibitors, the zero magnetic field. And we know that there are all these exciting recent experiments reporting this. And in particular, in twisted semiconductor MOT2, the gap of these quantum Hall states, quantum normed Hall states, are very large. For example, a filling factor 1, the gap measured by thermodynamic experiments is about 6 millielectron volt. Okay, and the quantization is observed up to 10 Kelvin, zero external field. So I don't need to go into any details about the detail of the system. What kind of a model we use, what kind of a DFT parameters we use, what kind of interaction we use, what's the nature of the ground state. All we need to know is that this is a semiconductor with an effective mass that is 0.62 electron mass. And this immediately tells me that the maximum possible gap is the following. It just depends on 1/m times the Morey unit cell area. Okay, and that is plotted here. The bound as a function of the twist angle. And so you at 3.4 degrees, for example, the maximum possible gap is 25 millielectron volt. The experimental report here is about 6 millielectron volts. So it's still some distance from the possible gap bound, but it's the same order of magnitude. Or you can look at you can apply this also to a non-interacting continuum model. You can use any parameter you like, and here I collect results for different DFT calculations. And again, right, these dotted these data points all fall below the bound. Okay, so I'm going to then stop here, and to summarize, I've shown you that there's relations between the energy gap of insulator and the thermodynamic response, in particular the dielectric constant, and relation to the topological invariant, the Chen number. I think really brings together topology, quantum geometry, and energy gap. So there are many interesting questions, and I list some of them here. And one thing I want to say that this reminds me a bit about in geometry, one of the quantities we characterize shapes is topological invariant, like genus. But also, when you go beyond topology, when you think about geometry, we sometimes ask questions like minimal surface, right, of a 2D surface is bounded by a particular boundary, and the boundary may be topologically non-trivial, and that actually can impose constraints on the area, on minimal surface area. So the topological bound on quantum metric is analogous to that. And finally, geometry and topology are all ground state properties, but quantum mechanics also tells us that the length is related to energy. So it's quantum metric. Didn't have time to go into this. Quantum metric is related to localization length, okay, intuitively speaking. Then the uncertainty principle tells us if you confine particles within a length scale, you have to constant energy. So energy and length are related. That's how energy gap enters. So I'm going to stop here. Thank you.
So it seems like when you were talking about the topological gap, you decided to adjust your density and mass. So what if you do the same for your thermodynamic gap?
Absolutely. So this is related to the question, is there a better bound on the optical spectral weight? So when I look at the topological bound, I use effective Hamiltonian. I could use a full Hamiltonian. In that case, the bound is just too loose. Right? So I switched to effective Hamiltonians. The same can be applied to thermodynamic bound, dielectric constant bound. If I have a nice, accurate, effective model for the system with a certain range of energies, then one can actually look at the optical spectral weight. And instead of n over m, where n is a full electron density, now n may be just the valence electron, for example. Right.
It seems like the bound would shift down quite
Will shift
dramatically.
down. It could,
And you're already kind of close, like
for some material, it's very close for boron nitrogen. This is why it's a great. We didn't expect it to be so good. Let's put it this way.
Could I ask you a question about each of the bounds? So about the thermodynamic one, you basically put it down as a bound on a gap given epsilon.
Given epsilon.
You can do the other thing, right?
You can also use it the other way. So I would say in that case, it's more like a universal relation between the energy gap and the dielectric constant.
But then you have dielectric constant, a Kubo formula in which all energy denominators you substitute with the smallest one. So that's an upper bound. And you have a bound on the matrix elements from the sum rule. And that's your bound.
Well, so if you look at the relation, right, the relation tells you that you can give you upper bound to the energy gap using dielectric constant. And you can also use the same relation the other way around to give you a upper bound on the
polarizability given the gap.
Given the gap, yes.
Right, and there is a bound because matrix elements of the dipole moment are constrained by the sum rule. That is it. That kind of takes magic out of it a little bit, no?
Yes.
Right.
I mean,
So
this derivation is very simple, right?
right. So and then this churn. So if I have a two-dimensional churn insulator,
Right.
and I put it on a magnet,
Yeah.
that opens up a gap.
Right.
And I have some magic device that cranks up magnetization of this magnet indefinitely.
Yeah.
So it would seem that the gap would go up
It doesn't.
indefinitely. So you say that it doesn't.
doesn't.
So
It doesn't.
what stops it?
What stops it? Because if your energy gap is too large, right? There's a single this way localization length, right? If you think about the non-interacting Hamiltonian, the energy gap is related to localization length. If you want a very, very large energy gap, it means that the localization length is very, very short. But we know that in the Chern insulator, right? In the Chern insulator, if you have a non-zero Chern number, particles cannot be localized to be smaller than lattice constant, because that would give you a trivial insulator.
But
That's
in terms of my construction, I take this magnet, I
It will
keep
be
increasing the spins in this
It will be
magnet.
topologically trivial.
So there will be another band inversion.
There will have to be another band inversion.
Necessarily
Exactly.
that will.
Exactly. That's another bad.
Yeah, just trivial question out of curiosity about this formula with extra square root for transverse part.
Yeah.
Yeah, you showed this nice table of comparison with a large number of materials. Is there any one over square root of epsilon dependence that you can see in the experimental data?
Yeah, so that's a good question. So if they have that dependence, they'll be parallel to this line roughly. This line has this. So you do see some kind of trend.
Sure, yeah.
The same. Yeah, so at least with the loving eye.
Or it doesn't matter, it's log scale.
Yeah, log scale, log scale. But I do have all the numbers here, right? So again, boron nitride is the best, 72%. But there are many materials on the order of
Sure. It was more interesting as this one over
the trend. Yeah.
Okay, let's thank you. Right, so our next speaker is Sodemann, and he's going to give you an update on forecasts.
Yeah, so thank you very much to the organizers for putting together this wonderful workshop and for giving me this opportunity to present our work here. So this work was done with these people. Likun is a postdoc in my group in Leipzig, and Oles, who is a postdoc with Justin Song at Singapore. And so basically, the kind of things that I'm going to review relate to this behavior of Floquet systems, okay, coupled to energy baths. And in particular, I want to focus on the question of what happens when those Floquet bands are partially filled. So basically, what is the nature of what would be a Fermi liquid if it was an ordinary band? And so we're going to encounter some very interesting states that I call the Floquet Fermi and the Floquet non-Fermi liquid. Okay. Yeah, so just a little bit of advertising about where I am right now. So I'm at the Institute of Theoretical Physics at the University of Leipzig, a place with great history, where Heisenberg used to be a professor, and where some of his PhD students were some of the people who laid out the foundations of solid state physics. Yeah, so Leipzig is very close to Berlin and Dresden. So if you're ever in the area, please let me know. It'd be great to host you. Yeah, so the talk is structured as follows. I will start with some overview of Floquet systems to try to satisfy Andre's suggestion to review the field. And then I will try to move on afterwards into discussing my actual work. So the work will be divided basically into two parts. I will try to introduce the notion of what I call a Floquet Fermi liquid. And the key for this part is that we're going to talk about Floquet bands of fermion systems coupled to fermionic baths. Okay, and we're going to encounter some state that is analogous in some sense to the ordinary Fermi liquid, but with some interesting twists. Okay, but then in the second part, I'm just going to couple the Floquet band to a bosonic bath. And we're going to encounter a very interesting state that I think has no analog in equilibrium. And I call it the ultra-critical Floquet non-Fermi liquid. Okay, so let me first try to set the stage for the kind of questions I want to address. So here we're talking about, what is the fate of many body systems when we're driving them continuously. So just imagine you have your system and there is is described by some Hamiltonian, and this Hamiltonian depends on a parameter that it's time dependent, that we're shaking in time, okay? So, when the parameters of the Hamiltonian are constant in time, we can open the textbooks and then we know what is the state of the system, what is the ensemble we should use. But when the parameters are changing in time, then this becomes a very hard problem, as we all know. And there is basically no general principles like entropy maximization to tell us what is the ensemble we should use. And so one of the kind of settings that you can consider is the setting of a closed system. This is not going to be the main setting, by the way, but just to prepare, why do we need to move onto this new setting of open systems? Let me first consider a little bit the discussion in a closed system. So imagine you have some, system that has a Hamiltonian. It's periodic, the Hamiltonian, some parameter is changing in time periodically. Then, basically by the second law of thermodynamics, if this change of the parameter of the Hamiltonian is happening at some finite rate, every time you return back, to the initial value of the parameter, if you do this at any finite rate, the second law of thermodynamics tells you that you have to be increasing the entropy of the system. And so generically what is expected and what has been discussed in the literature is that if there is no conservation laws and you just keep shaking the system and the system is a generic thermodynamically well-behaved system, then the system will just heat up to infinite temperature. There has been some discussions in the literature of how to try to avoid this in closed systems by having some form of hidden conservation laws. For example, if you have some kind of many-body localized state in which you can realize something like a discrete time crystal, but this is still very controversial. I don't want to go into that controversy. So in principle, there might be some way to get out of this, but generically, The point is if for a genetically thermodynamically well-behaved system, you will approach the so-called thermal death if the system is closed. So to make this question sort of well posed and interesting, we need to move from this setting. So we need to consider the system not to be closed, but to be open, to avoid this thermal death, to have some interesting late time steady state ensembles, okay? That are not just infinite temperature. So that's sort of the setting that I want to consider. So I want to consider a system that we are driving periodically in time. We're changing the Hamiltonian periodically, but it's also in contact with a heat bath, so that, you know, every time you add energy into the system in the form of work, then the system can leak that energy into the bath, and in that way it can reach some, you know, steady state with some finite energy density, but not infinite temperature. So some interesting late time steady state. Okay. Now, here is one of the key messages, okay, of the talk that I would like to emphasize in this slide. Okay. So it's one of the fundamental differences between equilibrium and non-equilibrium. Okay. So in equilibrium systems, the bath basically does not matter, right? So there is some class of systems that we're allowed to call baths. Okay, they have to be much larger than the system of interest, and they have to be weakly coupled to the system. But basically, you know, if I have fermions, let's say, of interest, and I'm coupling them to fermions or to bosons in equilibrium, if this coupling to these baths goes to zero, the system in equilibrium always approaches the same ensemble. Okay. And one of the key differences in the non-equilibrium setting is that this is not the case. So even in the setting in which two baths would produce the same ensemble, you know, in equilibrium, when you're out of equilibrium, two different baths might produce different late time steady states, even when they are weakly coupled and much larger than the system. Okay. So the question of understanding non-equilibrium states of matter becomes, in a sense, you know, richer and more complicated in the non-equilibrium setting, because it's not enough in order to describe the ensemble. The ensemble is not just depending on the Hamiltonian of the system and some you know, information of the bath, like the temperature only. It's going to be dependent also on the nature of the bath. So even if these two baths have the same temperature, but they are different physical systems, you might get different late time steady states. So there has been a lot of interest over recent years then on trying to understand what are these kind of ensembles that you get when you have, you know, fermions in a Floquet band, and they are coupled to some sort of bath. Okay, I just want here to, you know, highlight a few interesting things in the spirit of reviewing a little bit the developments in the field. And this is not comprehensive at all. I just cherry picked a few interesting examples. Okay, so one of the directions in which the field has had a lot of focus is on doing Floquet engineering of topological phases. Okay, so for example, there was an early pioneering proposal by Oka and Aoki that showed that if you just shine circularly polarized light in usual graphene, you will get a set of Floquet bands that have a finite Chern number. And so this leads, of course, to the possibility that maybe you can realize something like an anomalous quantum Hall state with light. But you know, the issue that this proposal was actually realized relatively recently in experiments by McIver and, you know, the group of Cavalieri. And but you know, the issue is that this, because of the shining of light, in a sense, the system is heating, so you don't get exact quantization. There is a non-trivial still steady state in which the occupations of the bands is not just like an equilibrium. You just feel, you know, the low energy band, so that there is no perfect quantization, but there is some observation of this anomalous Hall effect. There have been also, you know, interesting realizations, for example, in the group of Nugedic, of the observation of the with time resolved RPEs of the band structure that appears at the surface of topological insulators when you're shining light, so the Floquet band structure. So one of the points that I want to highlight here, maybe primarily aimed at the experimentalists in the audience, is that this type of experiments in Floquet engineering have relied on mostly on PAM probe protocol. So you're not really realizing a true steady state. You're shining light for some time. You shake the system, but you probe it very quickly before it sort of fully relaxes. So it has a transient time. So it's not a full steady state, okay? And one of the reasons this happens is that in order to enter the Floquet regime, the intensity of light that you have to shine is typically very large for the kind of frequencies that they use. So they typically use mid-infrared frequencies, and the intensity that you need to reach scales like the frequency to the 4th power. So if you plug numbers for this type of systems, for example, for graphene, you're using this type of frequency, you get that you need to shine intensities of 10 to the 12 watts per meter squared. So it's a huge amount of energy, and that produces a lot of heating. So you can only do that for a short amount of time, in a sense, and that's why this it needs this PAM probe type of approach. But so one of the things that I want to emphasize is that the key then to realize Floquet, interesting Floquet regimes, is one alternative is to go to much lower frequencies if you have very clean systems. Okay. And the other point that I want to mention here is that a lot of the emphasis in the studies in the literature have tried to focus on how to sort of mimic interesting equilibrium states with Floquet engineering, right? So how to realize a churn insulator in this Floquet setting, which is an equilibrium state of matter. How do we tweak the Floquet as best as we can to make it look like the equilibrium? But I want to sort of explore Floquet on itself a little bit more, right? So I want to let Floquet shine even more by itself to try to find things that have no analog in equilibrium. Okay. And in particular, one of the things that I want to focus is I don't want to think about insulators. I'm actually going to try to answer the question of, is there a precise Fermi liquid state in a Floquet system, with a sharp Fermi surface? Does the Fermi surface survive in this setting? Okay. And a lot of people have been working in Floquet physics over the years without calling it Floquet, right? So just a little bit like it was mentioned by Rafael in his talk, a lot of people have been working on altermagnets without knowing. So a lot of people have been doing Floquet physics for a long time without calling it Floquet. And one of the classes of experiments that I think is a very interesting Floquet setting, and it's really reaching this Floquet regime, is this set of experiments of microwave-induced resistance oscillations in two-dimensional electron gases. So this was actually, a remarkable phenomenon that was discovered by a local here, by Michael, who's there in the audience, and who has, studied this phenomenon over the years. And so the key here is microwave. So that's the point I want to emphasize for experimentalists. So if you lower the frequency, you don't have to shine very intense light. So if you're using the frequencies of microwaves, this intensity to reach the Floquet regime is very, it's much smaller. The other one was 10 to the 12. So it's a much smaller intensity. So you really can be then in the regime of the steady state. You're just shining light all the time, and you're just looking at the steady state of the system as it is. So the system just goes to its true, steady state. So this is a very interesting Floquet setting. And, is it calling it Floquet just a matter of making it sound sexier and cooler? No. So I'm going to try to convince you that the Floquet point of view actually sheds some insight on this phenomenon that I think has not been fully explored. Okay. So just to review a little bit the phenomena. So here, this dashed line shows the Shubnikov of the Haas oscillations of a two-dimensional electron gas in gallium arsenide. The dashed black line is, without light. And then when you shine the microwaves, the conductivity that you measure after shining the microwaves changes tremendously. So this is the resistivity in red when you're shining the light. And the system displays oscillations of the resistivity in this steady state even before you start seeing Shubnikov of the Haas. And there is various phenomena associated with this. Okay, so for example, an interesting phenomenon is, here is again an experiment done in a Corbino ring. So when you start increasing the power of the microwaves, and eventually these minima try to become negative and the system reaches this so-called zero resistance state. And that zero resistance state is believed to be associated with the formation of some type of current domains in the system.
So it says conductance. Is that right?
Conductance, yeah, conductance resistance. Sorry.
So zero conductance.
Zero conductance, same as zero resistance because you're in the whole region. And there has been a lot of theories over the years to try to understand this microwave-induced resistance oscillation phenomena, but I think there is a big elephant in the room, okay, that the field has not addressed, which is, what is the state of the two-dimensional electron gas at zero magnetic field? So I'm going to show you that this is a very non-trivial Fermi liquid light state, and that these oscillations, the microwave-induced resistance oscillations, can be actually interpreted as the Shubnikov of the Haas effect of this new type of Fermi liquid, okay? And so the other direction from which I came into this kind of questions is by trying to think about rectification in solids, okay? So there has been a long-standing controversy in optoelectronics, which is, it's a little bit of an academic controversy, but it's still interesting, which is, if you have a metal, okay, a very good metal with a very good optical gap, and you shine light that has a frequency inside of this optical gap of the metal, there will be, almost no absorption. So you will be in the transparency region. And then there is a question of, can you have current rectification even when there is vanishing absorption? So this metal needs to break inversion symmetry in order to have current rectification. So photocurrent, bulk photocurrent in a metal. Can it exist? So this is defined, as a DC current that you get to second order in electric field. So you're shining some electric field with some frequency omega. There is some rectification conductivity. So the question is, can the rectification conductivity remain zero even this limit in which tau goes to infinity? So you have a perfect metal with almost no absorption. You're inside of the gap, okay? And so the reason this is how I actually started thinking about these Floquet problems, because in the work that I did with Liang on the nonlinear Hall effect, if you take the predictions from our work, that predicts that this conductivity actually remains non-zero inside of the gap, even in this limit in which tau goes to infinity. So it was brought up to me the point that this was in contradiction with some old results at some point. So somebody had pointed out or had argued a long time ago that this was impossible, that you cannot have rectification inside of the gap of a metal in the correct steady state. But in the end, this is a question of what is the Floquet state in a metal when you're shining light in a metal, some kind of Fermi liquid-like state of this Floquet band. And the question is whether that Floquet state transports current or not. And the system eventually, you're shining light, sets in the steady state, does it have a net current flow? And so I'm going to try to argue that this earlier studies actually were wrong. They basically took the occupation of the Floquet bands to be the Fermi-Dirac, as if it was, and that was the key mistake. When you take the correct occupation of the Floquet bands, you actually can show very rigorously that this rectification conductivity is non-zero even inside of the gap. So all of these questions actually are connected, okay, to this. What is the steady state of Floquet bands for Fermis? Okay, so the first part, I'm going to take all of these, set of experiments and observations as sort of inspiration just to propose ideal models to try to answer these questions in a rather sharp and precise way. Okay, I don't want to hand wave too much. So I'm going to be dealing with some ideal models. Okay, and so the first part is going to be related to what is the steady state in a Floquet band when the fermions are coupled to a fermionic bath. So this is the part that we call the Floquet Fermi liquid. And to cut the long story short, instead of using the Fermi-Dirac occupation, when fermions are coupled to a fermionic bath, you should use something we call the Fermi-Dirac staircase, okay, which has multiple jumps at different values of the energy, if you wish. And as a consequence, this state actually features multiple Fermi surfaces with different areas. Okay, that's the one that we call the Floquet Fermi liquid.
And just a second, and the number of jumps is infinite or finite?
In a system with the number of jumps is always going to be finite, cut by some bandwidth. But basically, you take the Fermi energy and you displace it by the driving frequency, and there should be another jump there. The height of the jump might be very small. So the height of the jump will depend on the amplitude of the drive.
So when bandwidth goes to infinity, the number of jumps also goes to infinity.
Yes.
Really question that if I have a cling to the electron gas, right, by shine microwave, this comes zero. The fact that if I have a cling limit, then we really cannot excite the system.
These are good questions. So the center of this distribution is moving with the vector potential. So the center of mass of the system is still, moving like a single particle. So it's obeying the constant. It's the relative occupation. This shape is trying to describe the relative occupation. But the most interesting thing.
Sorry, just a quick question. So this presumably depends on the rate of inelasticity. I mean, even if you're seeking.
There is some settings that I need to define the models. I'll define the models. I'm just trying to give you first the punchline.
Okay.
But just to give you the punchlines quickly, in case I run out of time, because I'm running out of time. So when we couple the system to bosonic baths, we found something even more remarkable. Okay, so the steady state does not have jumps, but it still has some sharp non-analyticity. So it has some Fermi surface-like wave vectors, if you wish, in which there is no jumps. Okay, so the system, that's why we call it a non-Fermi liquid. It's a Floquet non-Fermi liquid. So there's a well-defined occupation with some non-analyticities in some surfaces that are these Floquet non-Fermi surfaces. But even the more crazy thing is that when the bath is at finite temperature, these kinks are still sharp. They don't smear out by temperature. So the system remains, the Fermi surface remains sharp, and the system remains power law correlated. So if you look at the 2-point correlation function of the fluid, it will still have power laws even at finite temperature. So that's why we call it ultra critical. It remains quantum critical in a sense at finite temperature. Yeah.
Is it how it was obtained? Is it analytics?
Yeah. Let me go. Okay.
Well, just tell us.
The second is very careful Boltzmann. The first is an actual analytical solution. So with fermions, it's easier, right? Because fermions, so basically you can imagine your system is some large tight binding model. The bath is another tight binding model. So the system as a whole is free, right? And the fermions are just tunneling into the bath sides, and then it can be solved exactly with fermions because the system as a whole is free. The only thing you have to assume is, the bath is at thermal equilibrium, let's say at -infinity. You prepare the fermions in any initial state, and eventually they will lose memory of the initial state and will relax to some state that is dictated by the bath. This can be solved exactly in various ways. You can use Keldysh. You can actually just solve this quantum mechanics and follow trajectory by trajectory. I'm not going to go too much into the technical details. These can be solved exactly without any cheating, okay? And so, but just to maybe give you a little bit more detail. So let me imagine a very simple bath that is just a collection of energy levels coupled to my tight binding model of interest. with some broad distribution of energy levels and flat energy bands. So I'm going to think of that as a featureless ideal bath. The conclusions remain by changing this. This is not crucial for the essential aspects of the conclusions. But if you take this kind of model for a bath, you can solve for the quantum mechanics of each initial wave function that you have for the system after integrating out the bath exactly. And it basically follows some kind of Schrodinger equation that is open, so it contains some dissipation, and it also knows about the initial condition of the bath, okay? The point is, you give me the initial condition of the bath, we can solve exactly the dynamics, okay? And so at late times, one can derive the exact ensemble that the system has. So you can prove that the system approaches this ensemble. This is the one-body Green's function, basically at equal time, so the occupation. And this is just some functional of whatever is your unitary evolution operator of the system in isolation. So you plug it into this formula and you can get what is the non-equilibrium steady state for the driven Floquet system now in contact with the bath. F0 here is a Fermi-Dirac distribution, okay?
Inti, that energy, is it actual energy or this is some quasi-energy that
The energy is the, you can think of it as the quasi-energy after doing some gauge fixing so that it has some unique label of the state. But a better way to think about the problem is think about momentum. So think about you have a single band and the electric field is uniform, so the momentum is still a good quantum number. So we can make all the states also with momentum so that it's more clear what occupation is really some occupation of some state, some physical occupation, okay? But so the conclusion basically in the setting of a band, so let me take a very simple band, so no berry faces, just like a tight binding model with, one orbital per site. And, we just drive the system with usual pile substitution uniformly. Then you can show that the steady state in the limit in which the coupling to the bath is weak becomes the following formula. Okay, so let me describe that formula. This is the steady state. So it's a sum of different Fermi-Dirac distributions. F0 is the Fermi-Dirac distribution evaluated in the Floquet energy of the state with momentum k, but shifted by multiples of the driving frequency. But the different Fermi-Dirac distributions have different weights, and these weights are the squares of the amplitudes of the Floquet wave functions. Okay, so you have this kind of shape, and the different jumps are the total jump is 1, but the different jumps are some number smaller than 1. This is the state we call the Floquet Fermi leak. So why can it help you understand that there is finite rectification? So this state is actually has a finite DC current. Okay, the way to understand this, imagine you have some band that has no K2 minus K symmetry. Okay, some metal without inversion symmetry and without time reversal also in this case. And so in equilibrium, the occupation is only a function of the energy. So two states that have the same energy have always the same occupation. The key difference with equilibrium of this formula is that the occupation is not a function only of the Floquet energy of the state, but it's also a function of the Floquet wave function. So two states that have the same Floquet energy, but they differ just by the Floquet wave function, will in general have different occupations in the steady state. That's the key difference from equilibrium. In equilibrium, you only care about energy. So when you compute currents, the current you can show that it's still given by basically the same expression that you have in equilibrium, but this energy here is the Floquet energy. You can prove this formula. But the key difference is in equilibrium, this function will be only a function of epsilon. So this can be transformed into a total derivative when you integrate over the Brillouin zone, gives you 0. So there's never a current in equilibrium as a consequence of the fact that the occupation just depends on energies. But when the occupation depends on wave functions, you cannot apply that. So generically, if you don't have K2 minus K symmetry, in a Floquet setting, the occupations will not be functions of only energies, and you will have a rectified current. So metals, this is the solution to the problem I mentioned of whether metals, where there is rectification even in the absence of absorption.
This is pure quantum mechanics. You don't need any kind of relaxation.
The steady state is a functional of the bath. Remember that point. So the actual value of the current will depend on whether I'm
So
coupling to a fermionic bath or a bosonic bath. But yeah, whoa. All right, let me hurry up. So how do I understand Miro? So Miro is just quantum oscillations of this Floquet Fermi liquid, because the different areas, you have various Fermi surfaces with different areas, and the displacement of the area is just omega. So it's just as if you were adding the Shubnik of the hash with different areas, of like if you had a multi-band metallic system with different areas, and then these different areas will give you interference of the frequency, and that gives rise to a beating pattern. So that is what Miro is this. You can understand it in this way as this oscillation of the amplitude. Bosonic bath, okay? 2 minutes, right? So bosonic bath, again, like very idealized model. So just take a tight binding model coupled to a collection of harmonic oscillators that have a continuum distribution of their eigenfrequencies, flat, and then just some coupling that is also energy independent. And so what we do here is we derive a very careful Boltzmann equation, okay? For this setting. It's a Boltzmann equation that has appeared before in the literature, so it's not like we're doing anything special in that sense, but we do it very carefully. So we have a very carefully derived Boltzmann equation in the sense that the rates, the scattering rates, are all determined by the Floquet problem and the properties of the bath. Okay, so for example, there is a scattering rate to go from K to K prime by emitting a boson into the bath. And this, knows about the density states of the bath. The only place that the temperature enters is to the scattering rates in the Bose occupation factors. And it has a matrix element that depends on the Floquet wave functions, okay? But it's just a very careful Boltzmann equation with absorption emission processes and so on. And so what we find is that the steady state is not that boring, as people always say, your shining light, the electrons just have a different temperature than the phonons. That's a very poor characterization of the non-equilibrium steady state. The system reaches a very non-trivial steady state that has a sharp non-analyticity. So it depends on dimensionality. In 1D is like a square root, as in a Lagrangian liquid. In 2D is like a jump of the derivative of the occupation, but it's still a very sharp non-analyticity. It depends on details of the bath, such as, whether it's ohmic, or whether it has a jump of the density of states. In this case, it's stronger. In this case, it's weaker. For example, this would have a jump of the second derivative, but it's always there. It has a very small area, this Fermi surface. The area of the Fermi surface is controlled by the size of the, this is displaced by omega, so it's controlled basically so that this area, the area of the Fermi surface equals the frequency of the drive for converting the right units. But the amazing thing that we found is that these kinks do not smear out with temperature. When the bath is even at finite temperature, these kinks are still there and they just disappear eventually when you go to infinite temperature. But the system, even at finite temperature, has sharp Fermi surface. We have computed correlation functions. So for example, if you look at the 2-point correlation function of the fluid, it still has power law correlations at long distances, so it remains critical. That's why we call it the ultra critical Floquet non-Fermi liquid. So with that, let me maybe close. And just to summarize, the steady state sensitively depends on the bath, but there are kinds of steady states. So when you have fermionic bath, you tend to get this Fermi liquid-like state, but with multiple Fermi surfaces. And with bosonic baths, you tend to get a non-Fermi liquid state, but where the Fermi surface remains sharp at finite temperature. Thank you.
So I have a question. So in the fermionic case, so you said it's like not interacting, but then I don't understand exactly what's going on. So I have fermions which are being driven by Floquet, and then they interact with additional sites which you consider the bath. But how is
why does it thermalize if it's not interacting?
Yeah, exactly. How is that?
Yeah, this is a restricted sense of thermalization. So it's like if I have a subsystem and I assume that the rest of the system is thermal, but I prepared initially my system in some excited state, the system will eventually radiate the initial state and will just thermalize with the rest. So if the bath was prepared in some weird initial state that is not thermal, I will never see a full thermalization. So thermalization occurs just because the bath is there, and the system just radiates the initial conditions and loses
So
memory.
you have to assume that the Hilbert space of the bath is large.
Yeah, you need to take the thermodynamic limit,
Yeah, okay,
right?
I
Of course, but and it's yeah.
To ask, looking at liquid part of your story,
Yeah.
can I view it as that near each of KF, there are many of them, I can think about fermionic green function with the residue proportional to the jump at this point. So you split just one green function into subset of fermions with smaller residue.
You could say that. I mean,
No, I'm asking about the result.
the quasi-particle energies are still the ones of the free system.
Right, but what about quasi-particle
But the
residue?
kinetics is non-trivial. So the way in which the states are occupied is non-trivial. So in the in the language of Keldysh, all the renormalizations of energies is not there, right? You have free particles, but the occupation is non-trivial. Only the occupation.
Yeah. So yeah, again, also about the first part, like in the photo emission experiments, when people drive the system and then do others, like nuclear experiment, this is replica bands.
Yeah.
And when I relate that experiment to the feature you are drawing here.
Yeah, I think it's related, possibly. I haven't thought carefully, but I think it's related. Yeah. Yeah, I think it's sort of that.
Intensity near each of the peak.
Yeah.
This is intensity near each of the peak.
All right, so let's thank Inti. We'll be back at 3:30.
Research, right, regular time.
Right. And Eugene is here as well. Like a reunion of sorts. You're such
And oh, that's right. The election reforms totally like not instructing the election. Okay, so my electrons are very strange beasts that respond to use the formula, you get the result. And then you say, wait, but the electrons actually create their own field. So it's sigma equal to E plus U of the electrons, which come from divergence of the side that when you consider dielectric and capacitor, that's what you do. But I think that's what This part, non-interacting.
A very simple model. The back is the boson.
Maybe that's.
I mean, if you just it's just the property.
我就是想你们对。
And everything is free. That's why it's really very simple, but it's good. Yeah, I mean, I have a style from this point to throw it out.
I don't know, it's over here. Just down. Right next to
Find the 30 minutes to do the first year.
Maybe it's what the name minus some. But it's
然后他的 my last day is frustrated，
okay.
因为如果只有1万的话，那就是一个非常强的 stability 在替在那个A 点6的起点3点。
Like a little bit earlier.
我那个品牌认为说
Or
就是有点
I pulled my shoulder in the shower to know. This is age. I just reached for something like this.
looking to focus on so-called calculations and
Lift an Apple pen.
that's
It's
he's
too
legit.
I tried to do this calculation, whatever I'm interested in my head. I just, unless it starts working, then it's terrible, right? Because then you cannot fall asleep right now.
Yeah, I don't know. I haven't looked at Facebook.
I don't know, it's just in the, whatever is in the, you're in the Facebook. Oh, we're just all like gonna go check together.
你要做 X， 要现在把铁路压下去，大家都
Я во вторник. Нет, я завтра, на самом деле, в понедельник мне я там назначил. Я, наверное, просто там, знаешь, просто домашку нужно акцидентом, какие-то мелкие сколько. Приехать из Дании на работу. Но если да, если ты хочешь что-то сделать, вечером какой-то будет ужин, полюбил,
What we need.
Так у меня украли лэптоп. И я воспользовался этим как поводом, так сказать. Да, мне я просто слишком новый, да. Интересно. Там этот Inti ну, вычеркнул. Какое-то это самое. Или я забыл его вписать. Я бы сюда еще вписал и Василия. Я помню, сюда вписал какие форматы, не мог забыть. То есть, я думаю, ну, может, ты его вычеркнул, не знаете, у них нет там, сказать, рождения мониторинга.
没有去来了。
回来了，回美国了。
Ну да,
哎，你现在来让姐姐聊这个
студент сейчас постдок.
就是你们都没有被考虑，就所以那个 Rugas 那个，他也没有说啥没有。哦，你是去年是吗？对，所以你现在是跟两年的意思。
Да, давайте, да. До встречи летом.
А,那每个人都不能去。
Мне кажется,
他不是很放养。
对，他这个概念是
Как-то жалко. Он, бедняга, перед этими воркшопами, там, если не что, не вытирает. Это как он письма уже можем написать тотально.
Нет, безусловно.
Ну и
哦 ，OK， 你来做，没错，可以做这个。你们是在搞编单体系里面搞？
Я имею в виду, хотя бы с людьми, так сказать, переписываться можно нам тогда. Они... Ну да. Может быть какой-то, знаете, как FTPI, райтап такой вот. О чем речь идет или просто получается?
你是不越来成 gas 是吧？
Ну да, какой-то оборот.
OK， 包括来说，
Ну да. Ну все будет.
At some point,
都会说，哎，
I'm staying with people at the same time. We're sharing an apartment.
对 ，OK， 那你是两次就没有跟 X 的那边。
Yeah, I saw that.
And it's great. We can finally have an in-person meeting.
先撑过一年就没事，先要撑过一年。 一般是3个月和1年，你看你超过3个月。不过它其实写的非常少，但是它变了。
我当面了还是有
对，有没有非常吓人？
我都有证据。
哎呦我靠！你要举报他吗？
我只说的你
maybe more
非常少，一般三个月会给一批人。
Yeah, sure.
像养缩是哪1年是吧？
What I don't understand is
他是传说中那个走掉的人。
啊，很多啊，走掉的人多了去了，他是其中一个，他是其中一个。
我也差点。
这是其中一个，就是他是1年走的，你们居然不知道他？
没有。
OK， 那我你是谁的谁？哦，来了吗？我现在是在第2做保护，做保护吗？跟陈萌还是？
我跟他在聊，但是我不算他的。
OK， 那你可以给他吗？OK， 所以是 free for all。这口碑感觉怎么样？哦，我在这看，哎呀，我靠，有道理。
好。他是那个票的，他现在在那个。
就是这样。
哦，你好。
他之前在加拿大的一个。
就在那不然的话，我
and you will be able to found with small amount of use our well, the constant depends again on the.
It doesn't seem much fun, right?
Yes, so if you go then the bound of marginal and excellence there in normal variable.
Yeah. Will relate to something. But there's no here.
Yeah, there's no. Yeah, now if we're in the. Some public relations. Because as like you have, like whatever. Issues are good.
Just go on. No, it's because yeah, so basically then it seems to have like slow convergence, but maybe I know because mine didn't happen.
Yeah. Okay, yeah, sure. Yeah. So it's specific to, yeah, it's, I would, yeah. Yes. Like if you can have a, like, one of the two case system.
Yes.
0.
Yeah. Thanks.
Yeah.
Yeah, basically something like what is continuity.
you put this boundary condition in mathematics. Normally people don't really have this, they consider this 2D thing.
No, I mean, there's a issue.
That purely classical thing, how should I figure it out? That's what's the name of this boundary condition? What happened? Yes. Can also we not convert it.
Yeah, some couples.
Yes. Already left. Have a decision. Yeah. So what? Things that don't deliver values. One message. Yeah. Oh, okay. I think like. I think it's probably. It never proves. to find out like I think I solve the problem. I solve it. Also don't understand what's an argument about the long offset or should be. I don't understand the Andreev. Ready to do the calculation. Yeah. No worries. Yeah. Thanks. Я могу нажать, там конкретно я могу пускать одна. Самое позднее, самое агрессивное, после матча. Они плохо написаны, только я понимаю. I'm not ready for the calculation, but it's, yeah. I really don't argue with like the first one. That's
Okay, so let's start. This is our final session. The first speaker is Anton Andreev from University of Washington, and Anton will tell us about the Debye mechanism.
Okay, thank you, Sasha. So I want to start by thanking the organizers for the invitation to this wonderful workshop, also for encouraging the speakers to give introductions. I think it worked. I feel like I learned a lot. My talk will be about, fairly introductory, the whole thing. I will discuss the Debye mechanism of dissipation in superconductors and how it manifests itself in microwave absorption. So this is based on a series of works done together with Boris Spivak, my former student Mike Smith, who is now a postdoc at Argonne with Ivar, and Tony Liu, Boris's current student. So the phenomena I will discuss today are going to be related to a qualitative difference between the kinetics of quasi-particles in superconductors and kinetics of electrons in normal metals. And the difference is that in superconductors, the density of states of quasi-particles can depend on time when you apply an AC electric field. And the reason is that the density of states can depend on the superfluid momentum Ps due to depairing. And as a result, when you subject the superconductor to an external microwave field, acceleration of the condensate will cause the dependence of density of states on time. And that's the aspect that is absent in normal metals. So one way to kind of understand, maybe qualitatively, or look at it from a different viewpoint, is the following by considering clean superconductors. So in this case, the quasi-particle energy has this standard BCS square root dependence, but in the presence of a supercurrent, there is this boost term, which is proportional to the condensate momentum, and the coupling of the condensate momentum to the energy occurs by a current. So I want to know that this Vp is not the group velocity of a quasi-particle, but rather it's the normal state velocity of the electron. So the coupling to the condensate momentum couples occurs via an electrical current. And so similarly, if you write a current density in terms of the non-equilibrium distribution function of quasi-particles, each quasi-particle contributes to the current, the charge of the electron times the normal state velocity. So then you see that in the presence of a superfluid momentum, the energy contribution of a quasi-particle and its contribution to the current are correlated. And you might suspect that therefore relaxation of the current might involve energy relaxation, and therefore you can expect that energy relaxation time can appear in the AC conductivity. And so I will discuss like when this can occur. Yes, please.
Even for follow-up. P is PF. So, right? Momentum is called
Yes,
PF.
yes, right. This is the Fermi
Trying to
velocity.
understand what is the fight about? Normally, Fermi energy is much larger than the gap values, right? So change of PF due to change of momentum due to superconductivity is a small effect. Are you fighting?
Good. I'm talking about, I'm saying that the condensate will be accelerated. The P Fermi can stay constant. You can forget about the acceleration of the quasi-particle, but the condensate will accelerate, and that will change the energy of the quasi-particle. So one way to think about it is that the spectrum is formed in the reference frame of the condensate, and then you boost to lab frame, and that's this boost term. Okay, so that acceleration of the condensate is where the effect comes from.
Maybe it's worth saying that P and P sub S are completely different quantities.
Exactly. I will. It's kind of. I will show the precise formula. PS is the. It's the. Okay, it's the gradient of the superfluid phase, covariant zero. Okay. So then, good. Now here's the kind of review part. What I'll need, I will review with the basics about absorption of microwaves in normal metals and superconductors, starting from normal metals. So in this case, what will be important for me is that two relaxation times at low temperatures. So the momentum relaxation for normal electrons is dominated by elastic collisions with impurities. And then energy relaxation is mediated by electron-electron or electron-phonon collisions. And typically at low temperatures, the inelastic relaxation time is much longer than the elastic one. And this can be kind of several orders of magnitude in the low temperature. So this is important that I will look for the effects that are kind of proportional to this long time. Okay, so then in normal metals, you absorb microwaves penetrate to skin depth into a metal. And so if the frequency is smaller than the elastic relaxation rate, the conductivity, the AC conductivity is basically equal to the DC through the conductivity, and therefore the absorption coefficient of microwaves is proportional to the through the conductivity, which is proportional to the short elastic relaxation time of the electrons. And the long inelastic time plays no role. Okay, so now moving on to superconductors. Again, I want to stick to the low frequency regime where the frequency will be smaller than delta. And for simplicity, I want to also assume that temperature is also greater than delta, but although that is inessential. So then the AC current in superconductors is written at low frequencies as a sum of the superfluid contribution. So here NS is the superfluid density. PS, finally, here's the formula for the superfluid momentum. It's grad chi, the phase of the order parameter, but minus this vector potential. But now in the presence of a microwave radiation, the condensate undergoes acceleration. This is the condensate acceleration equation. So PS becomes time dependent. This is only, the supercurrent is the leading term, but then there is also a term proportional to PS dot, time derivative, and the coefficient is the AC conductivity. Okay, so this AC conductivity microscopic studies began almost immediately after the advent of the BCS theory, starting with a paper by Mattis and Bardeen in '58. And two mechanisms are possible. For frequencies greater than 2 delta, you can excite quasi-particles, but at low frequencies, absorption exists only due to already thermally excited quasi-particles. And then close to TC, so what the main point is it's still the dissipative conductivity is proportional to the momentum relaxation time of quasiparticles, and that's the kind of elastic relaxation time. So in particular, close to TC, this AC conductivity of superconductors is practically equal to the Drude conductivity up to kind of small corrections. And again, the inelastic relaxation time does not appear in this result, despite what I alluded that could be the case. So nevertheless, I'll show that under some conditions, the long inelastic time does appear. To explain that, I want to introduce the microscopic mechanism of the appearance of the inelastic relaxation time. This is the Debye mechanism, which was studied by Peter Debye when he considered absorption of microwaves in polar molecular gases. And the mechanism, in a nutshell, the essence of the mechanism is the following. So this ugly curve, imagine that it's a kind of equilibrium distribution, occupancy of the levels, and the green bar is the kind of the location of the level, and its height it gives it the equilibrium occupancy. But so now if in the presence of microwave radiations, the molecular levels become displaced due to kind of polarization with energy, they start moving up and down in energy space, and therefore an initially equilibrium occupancy becomes non-equilibrium. That sets off inelastic relaxation. The rate is proportional to the inelastic relaxation rate, and therefore you can show that at low frequencies, the average kind of non-equilibrium occupancy of a given level is proportional to the amplitude of the microwave field and the inelastic relaxation time. And then you can get the microwave conductivity, the real part, by equating the Joule heat to the Andreev production rate. And the result is that you get the conductivity, which is proportional to the energy relaxation time. That's the Debye mechanism. Okay, so how does it arise in superconductors? So this can be understood as follows. Let's say this is a kind of schematics of the BCS peak. Let's stick to S-wave superconductors. So you have a sharp kind of singularity in the absence of PS, but due to the superfluid momentum, depairing will round the BCS singularity, and when the magnitude of this superfluid momentum will oscillate with the field, the width of this broadening will change, so the levels will move up and down with energy, setting off inelastic relaxation and giving a contribution to dissipation proportional to the inelastic relaxation time. So why doesn't it show up in these classic results? The reason is that the density of states is a scalar quantity, so it can depend only in the square of the superfluid momentum, not on a vector. And therefore, when you take a type derivative of the density of states, you need, if you want to get this Debye mechanism in linear absorption, in addition to the vector, the electric field, you need also a DC superfluid momentum. So this contribution arises only in the presence of a DC equilibrium current, but it does not arise in the absence thereof. Okay, but so let me now discuss when we can expect this contribution, and starting with the kind of simplest example. So let's consider a uniform superconducting film. So thin film, normal incidence of microwaves, the microwave is in plane, and I want to stick to the low frequency regime, where both the frequency of the microwaves and the inelastic relaxation rate are both much, much smaller than elastic one. So in this regime, it turns out that you can construct a very simple description of this Debye contribution to conductivity. And the reason is that the non-equilibrium quasiparticle distribution function is independent of momentum. So momentum relaxation is fully happening, and therefore the quasiparticle distribution depends on the energy and time. Okay, and then you can get the kind of the Boltzmann equation, set up the description. You can construct it using kind of two following ingredients, using the conservation of the quasiparticle energy levels. You can view them as a gas, like Pichuka's gas in one dimensional. So this density of states is the density of particles. They move up and down. This is described by the continuity equation. And here the level velocity, little v sub nu, just tells you how, which way and how fast the level moves. And that level velocity is proportional to the microwave field and the sensitivity of this level to the changes in PS. And that sensitivity is this vector quantity, which has units of velocity, length per unit time. And you can express it if you know the dependence of the density of states on PS. And then, so if the quasi-particles were just entrained, would move together with levels, you'd get another continuity equation for the quasi-particle distribution function. But in the presence of energy relaxation, there is an additional source of evolution, which is the inelastic collision integral. And so you have this kinetic equation for this energy-dependent distribution function of quasi-particles. If you solve it, then you can get the conductivity, AC conductivity, by averaging the work done by the electric field on the non-equilibrium population of quasi-particles. And therefore, this way you can define both linear and non-linear conductivity. Okay, so then let me start with the, so in that sense, it's a kind of very general description which works for both, I mean, any type of disorder, strength, and also any symmetry of the order parameter. Yes, please.
Earlier you said in order to see this effect in linear response, you need a high DC current.
Yes.
But now does it, this is still linear response?
No, oh, good. So
Sorry.
two things. So yeah, so if good linearity comes in this, how do you treat the driving force, right? So you can still get a nonlinear solution. So my claim is it it's my definition of the nonlinear conductivity. If I solve this equation for the collision integral in the nonlinear approximation, right, that will give me nonlinear conductivity. But I will use it in two ways: either studying by linear conductivity in the presence of a DC's current, or in the nonlinear regime. Okay, so let's start with this linear absorption. So the setup is that we have a DC superfluid momentum, and then an additional time-dependent correction, which is proportional to the microwave field. Because we are in the nonlinear regime, we're going to linearize the Boltzmann equation to deviations. And so another important point is that the main contribution to this Debye absorption comes from quasi-particles in this broadening of the BCS peaks. It's a narrow energy interval. Whereas if your temperature is greater than that energy interval, then the typical energy scale involved in inelastic collisions is a water temperature. So the particles basically leave that region, go to the bath, and therefore you only need the out relaxation term, and this relaxation time approximation becomes virtually exact. Okay? So it's what it meant is tau for these particles in this region. So anyway, yes, please.
Just a quick question. So in general, the distribution function it's in number space in superconductors. So it seems that you somehow condense only to a single distribution function. So is there an additional assumption of some sort? Because let's say the supercurrent itself is determined by
it's good with number space. You're talking about already. In a way, you're talking about wave functions, right? So here, the energy defines that wave function, and so this number it can be, in a sense, it's hidden in this tau. Maybe another thing that you can have if you have this
distribution, the kinetic equation for Keldy's block, and Keldy's block is itself a matrix.
Yes.
So then,
but I'm saying that the wave function does not matter for me, only the eigenenergy, right? So what it looks like, UV coherence factors, they're not important. What they enter this inelastic relaxation rate. So if you want to evaluate collisions of quasi-particles with phonons, that probability and the rate depends on these coherence factors. But okay, sorry. Yeah, anyway, just linearize it. Let me just present the results. Then for this linear conductivity, the way it's presented here, it's a ratio. It's written as a ratio of this Debye contribution to the conductivity to the Drude contribution. You see that there is a large factor ratio of relaxation times, which is assumed large. Another noteworthy feature is that this Debye contribution exhibits a strong frequency dispersion at much shorter frequency scales associated with the inelastic relaxation rate. That may be used to probe the rate, measure the elastic rate in superconductors. And then so the remainder is a kind of definite integral that in some, anyway, assuming the temperatures are larger than delta, its simpler form, there's a more general expression. But the important point is that it's expressed in terms of the density of states at PS bar, this DC superfluid momentum, and the square of sensitivity. What I should say about this is that even though it's written as a scalar, the Debye contribution to the conductivity is strongly anisotropic. It is present only for the longitudinal geometry when the electric field is parallel to the DC current. And in the transverse geometry, it does not appear. And the reason is simple, that if DC supercurrent is pointing up, the transverse field does not change the magnitude. Okay, so there is a kind of characteristic anisotropy. And this formula, as written, is generally applies to any kind of strength of disorder and any symmetry of the order parameter. We've discussed D wave in this paper. I will not do it. I will stick to S wave superconductors. Yes.
So is there a way to reduce the necessity of remove the necessity of the DC current with some breaking of some other symmetry? Is it just
yes? And I will discuss that here. Okay, then going to DC. What I want to, this is a S wave square root singularity of DCS, and the way the magnitude of the broadening due to the superfluid momentum and the shape as a function of energy depend on the disorder strength, how dirty the superconductor is, and also the magnitude of PS. And you can distinguish between a diffusive regime and ballistic regime of microwave absorption. So ballistic regime, roughly speaking, is the following: that you have a certain width of the broadening, which is given by V Fermi PS. That's the depairing broadening. And this width, if it exceeds the momentum relaxation rate, elastic rate for these quasiparticles in this region, that is the ballistic regime. And it occurs only if this parameter delta V Fermi PS tau elastic squared is greater than 1. So it can only be realized in clean superconductors where delta tau elastic is a large parameter, but that's not enough. Also, the pair breaking should be sufficiently strong. And if in the opposite regime, diffusive, where the momentum relaxation rate is shorter, greater than the width of this window, the quasiparticles participating in microwave absorption diffuse. And in this case, the broadening has a different shape and different magnitude. Okay, so then let me start with the results for the ballistic regime. You can evaluate the integrals, ratio of relaxation times, Lorentzian frequency dependence. And then, so you see what Liang was asking. So you see that when DC superfluid momentum vanishes, you get nothing. And then you get a square root non-analytic dependence on the DC superfluid momentum. So these are small parameters under our assumption, but they can be compensated. We have several orders of magnitude to play with. So in principle, this Debye contribution can be of the same order or even greater than the
This is the DC conductivity you're talking about?
Sorry?
This is the DC conductivity.
Well, there's omega, so you can take it to a very small limit. When the frequency becomes smaller than the inelastic relaxation rate, it kind of becomes DC, but still, all it means, you have to still have this finite frequency, right? You need to drive it, otherwise there is no dissipation. So I'm always talking about a kind of small correction to the supercurrent, which is reactive, does not dissipate, but that small correction is what I'm discussing. So there is always a shunt by a superfluid current. But the absorption is all from here.
But suppose I use the time-dependent Ginzburg-Leiner equation. You can't get this contribution from that.
No,
but that's at much lower frequencies.
Exactly, right.
Okay.
Okay, so then now this was just a pure limit. If you have add disorder, what you need to solve is Gorkov equation. What you need to find is really the dependence of the density of states on PS. In general, you get a quintic equation for an arbitrary ratio of disorder. It reduces in the clean limit to a biquadratic equation. And in the disordered, diffusive regime, it becomes cubic. And non-surprisingly, if you start from the dirty regime, from the Usadel equation, and then you add pair breaking, you also get the same cubic equation starting from the Usadel equation. But I want to say that even in clean superconductors, in that sliver of the energy window relevant for the microwave absorption, that equation works. It's always the same Usadel type. Anyway, and then you get the following results that somewhat surprisingly, the dependence on the DC superfluid momentum is still non-analytic. It's PS to the power 4/3, same frequency dependence. And here I want to comment that the first people who identified this mechanism proportional to the inelastic relaxation time in the presence of a DC supercurrent were Ovchinnikov and Isakyan. They used the Usadel equation and then Larkin-Ovchinnikov kinetic equations, but they treated the Usadel equation perturbatively, pair breaking term. D is the diffusion coefficient, so dps squared is pair breaking. They used perturbation theory and got a result that is proportional to dps squared, but perturbation theory breaks down near that singular density of states. That's why we believe that that's the reason for the discrepancy. We believe that our result is correct. Note that it's, because of this non-analytic dependence, we get kind of coming to nonlinear conductivity. I'll comment. One more. Okay, so about a possible experimental observation, there was a fairly recent experiment in the group of Carl Berger at MIT. They looked at this kind of meandering superconducting wire, niobium nitride at T over TC 0.2. That's the schematic picture of the device. That's the scanning micrograph of this meandering wire. And this is a quote from their paper. So at finite current, the measured sheet resistance is several orders of magnitude larger than the theory would suggest. The theory they used is based on Mattis-Bardeen, and the sheet resistance is the 1 over the thickness of the film, and then it's basically the inverse real part of the inverse conductivity, which is proportional to the real part of the conductivity. So sigma 1 is the real part, sigma 2 is the refractive part related to the superfluid density. So here, that's the theory prediction. And now as they increase the current, you see that it's a significantly larger result. So it's possibly manifestation of this Debye mechanism. Okay, so then now let's move to the nonlinear regime. Assume that there is no supercurrent. You can just solve the equation, go through the formulas. So roughly speaking, you get the same results for nonlinear conductivity as if you took the linear results and you replace this DC superfluid momentum with the amplitude of the AC momentum. Okay. And the results are in the ballistic regime, you get square root of E omega, just like square root of PS. Here it's E to the power 4/3. And because of this non-analytic dependence, it's more significant than Okay, so now going to Dima's question. So do you actually need a supercurrent? And really no. So by symmetry, all you need for linear absorption is the presence of another vector that breaks time universal symmetry. So as Dima suggested, you can't just either have a system with a spontaneously broken time universal symmetry and the vector, or you can induce it by applying an external magnetic field. So we considered a case of a film with an in-plane magnetic field. However, the magnetic field is a pseudo vector, so you actually have to convert it to the polar vector. So you need a non-center symmetric conductor. What we consider this is a 2D conductor, non-center symmetric with spin orbit coupling. Here, in such materials, there's a so-called Edelstein effect, magnetoelectric effect, which means that even in the absence of supercurrent, if you apply a magnetic field, you develop a gradient of kind of winding of the phase of the order parameter. So it gives you a finite superfluid momentum at zero current, but you cannot simply just use this Edelstein effect and put this PS induced by the magnetic field in our results and get the correct one. It's not quite that simple. You need to take into account both. And anyways, we just considered superconductor with linear in momentum spin orbit coupling of Rashba and Dresselhaus type by some combination. And we just compute a bunch of diagrams and get the following results. For the ballistic regime, again, now ballistic is now defined by the strength of transversal symmetry breaking or diffusive, and you get these results with the same characteristic anisotropy of this Debye contribution on the relative angle between the in-plane magnetic field and H. And that optimal angle depends on whether you have a Rashba coupling or Dresselhaus. Anyway, and the results, you can transcribe them, basically. Sasha, how long do I have? Fine, okay, good. Oh, actually, let's say virtually, will go faster than I thought. So you can get the same mechanism also in SNS junctions. So here, let's say, suppose you have a superconductor normal metal superconductor junctions, you have subgap states in the normal region. Their density of these Andreev states depends on the difference of the order parameters, chi1 minus chi2. And if you apply a bias to the superconductor, then the phase evolves according to the Johnson relation with the voltage. And this causes the time dependence of the density of states, and you get inelastic realization. And you can just use our not quite results, but I will not describe the formalism. But the point is that because of the long inelastic realization time at low biases, if your drive is slow, you get conductances which are proportional to the long inelastic time. And so therefore, there is a low bias regime in SNS junctions where transport coefficients are much greater than they would be in the normal metal. So if you have a bias junction, then the IV characteristic is with N shape with this, the peak can be high. And if you now current bias the junction, again, you fix the current, but there's subtlety. There are 2 points where the phase difference is equal to 0 and pi, where you have to cross quickly cross through them. But away from these regions, the phase evolution is slow, and therefore it's amenable to our description. And so then what you get is a very low bias currents. You get a kind of a foot in the IV characteristic for current bias junctions, and then you kind of transition to the normal regime where the conductance is basically described by the conductance of the normal region. So a possibly related experiment to this mechanism was earlier performed by Tinkham, not on SNS junctions, but on weak links, where there was a groove cut in a superconductor, which could reduce the superfluid density or the gap in the groove. And what they found is that for current bias junctions, the IV characteristic was the following. So you start with the normal state, you think that you go to a critical current, but then there's a foot with much smaller voltages, much greater conductances, but really the system is still in a dissipative state. And so this could be, so what we are saying is that they have an explanation in terms of a kind of time-dependent Ginzburg-Landau dependence of the gap, but that is not necessary. So in SNS junctions, the same mechanism should be at play, and therefore, it may be important for identifying what the true critical current is. It can be actually lower than this upturn here. So maybe important. And another thing that I didn't put up is that you can also study non-reciprocity of the dissipative regime. If you know the phase dependence of the density of states, if you break transversal symmetry, it becomes non-reciprocal, and therefore these IV characteristics here, they can be non-reciprocal, they can be odd in bias and in the magnetic field, and that can also be studied within this formalism. And the final thing I will say is that the ingredients for the existence of this mechanism also are present in the vortex state, in the mixed state of superconducting films. You have superfluid velocity to begin with, and therefore this mechanism is also present when you study microwave absorption in the presence of a vortex lattice. However, here it's important to take into account the distortion of the vortex lattice. So in an ideal lattice, you have this kind of axially symmetric distribution of the superfluid velocity. So if you ask, so in some sense, this Debye absorption comes from quasiparticles trapped inside the vortex core. So what is drawn here is energy and the distance to the vortex core, and this is the threshold of where the quasiparticle spectrum is, the bound. So then if you have the symmetric distribution, basically this velocity averages out, you get nothing. But if pinning distorts the vortices, you have this kind of distortion, and then additional acceleration of the condensate by this field creates a contribution, Debye contribution to the density of state. And this was studied in these papers. And let me then stop and summarize. So we constructed a very simple description of this Debye contribution to conductivity. I presented the theory for uniform systems. This contribution is proportional to the long inelastic relaxation time, is anisotropic, arises in the presence of time versus symmetry breaking. This may be useful for identifying unconventional superconductivity with Brocal time versus symmetry, using microwaves for doing that. And the final thing I want to say is that this Debye contribution breaks Mathiassen's rule. Here, the conductivity, Debye conductivity should be added to the Mathias-Bardeen conductivity, not the resistivity is added. Okay, thank you.
You mentioned vortices, so it's different from the conventional Bardeen-Steven mechanism?
Yes.
So what is it? The difference?
Right, so I think, good, so Bardeen-Steven is flux flow, right, first of all. So
yeah, it's normal course, so even
good,
right.
yes, good. So then what I would say is that I only discussed this uniform situation where you can only relax the non-equilibrium distribution via inelastic relaxation. But if you have a, like, suppose that you start, you move this vortex, you generate a non-equilibrium energy distribution, but then it can relax via diffusion, right? So then whether you have a flux flow regime or just kind of shaking of the vortex, this asymmetric part of the non-equilibrium energy distribution can relax via diffusion. So in a way, Bardeen-Steven, and there are two things. So if you ask what is the non-equilibrium part of the superfluid velocity due to the vortex displacement, it goes as 1/r². And that's dominated kind of by the core, right? And if you want to be in the London regime, there is also an additional part of kind of superfluid velocity PS, which does not decay. And therefore, there are quasiparticles even at close to this percolation threshold, which are still non-equilibrium, and their diffusion time is much longer. So that's what we're doing now. So there is a part that is still diffusive in origin, but involves times kind of much shorter than the core. And there is also, in the presence of the distortion, diffusion cannot heal completely the distribution. You also need energy relaxation because the average goes kind of up and down.
Does it mean that the dependence on frequency will be different? I mean, is there
right? There is a, yes, it's involved. So there's a kind of small coefficient. We cannot claim that, okay, let's say that there is a diffusive part of the relaxation. So Bardeen-Steven, I would say, is the kind of diffusive part, which is associated with this 1/r² and it dominated by the core. But there's also a long part, which is diffusive, that has a different frequency dispersion. And there is yet another part due to inelastic relaxation time with even much dispersion at much weaker frequencies.
Explain again, just on the point of IV curve in the voltage bison. What says that J max?
Good. So that one.
Yes.
So initially you increase the voltage you get the current because you have this is linear conductivity. But then because of this 1/ω² Lorentzian shape, the Debye contribution peters out at larger frequencies, right? And at some point, the frequency becomes too fast for the inelastic polarization to be effective, and then everything is dominated by diffusion, and then you just go to this kind of normal state.
It's a new laptop and it's so dark up here. I can't see the buttons. All right, a second. Let's see. This is it, right? Oh, that's better. Thank you. Let's try this one.
Yeah.
There we go.
Yeah.
Oh. Okay, it's time to wake up. So dark in this room, I'm trying not to fall asleep myself. Okay. Okay, so I enjoyed all the talks today, and I'm appreciative to come here and be in a much more comfortable atmosphere than the March meeting that's starting tomorrow. And I also took seriously the request to keep this general and introductory. And in fact, I appreciate that probably a lot of you are not familiar with this material or the developments and so on. So most of my talk will be just sort of a review of what's been happening in this field, and I'll highlight some of the work we've done on the way. Okay, so okay, so there we go. Okay, so first of all, acknowledge some collaborators that have been working with us quite closely on this material. In particular, Sheng Ren, who discovered the superconductivity in this material about 5 years ago when he was a postdoc with Nick Butch, who's a NIST researcher that works closely with us at Maryland as well. And then over the years, we've worked with several people, including Daniel Achterberg on theory and Andrei Nevedomsky and a bunch of experimentalists. Won't go through everybody. Most recently, some ultrasound work I'll highlight at the end with Brad Ramshaw, and some STM work with Vidya and Seamus. There's 2 sessions at the March meeting. So tomorrow morning and Tuesday morning, I don't know where they are, I haven't looked, but they're invited sessions. So I invite you to come and see all the talks there. And then there's a session on Friday. So I'll be here all week because of that. So early on, we reported this material, and in the first year or two, there were some amazing discoveries, not only the superconductivity, but the high field superconducting phases, reentrant phase, and so on. There's a lot of fanfare. And I like to show, I've been showing this slide for a few years now, but, I had to do an update slide because it seems that the most interesting thing is that the graphics are getting more exotic as we go along. So I don't know what that is supposed to be. It's supposed to be some quantum computer, I guess, with uranium telluride and, quantum leaps and so on. I like this one because you can't see it, but it's the medical breakthroughs section of this journal. So even medicine we're affected. It's amazing. Okay, but as you see here, this actually just appeared on Friday, so I'll flash some new data about this so-called Lazarus phase, the high field phase, as we go along. It all started with Sheng's discovery, and this is actually the data. So if you're wondering what a real superconducting transition looks like, it looks like that. None of this funny business in LK99 and so on. When I first saw this curve, I thought, okay, that's kind of neat. It's a new superconductor. We'll do some measurements, usual thing. And it wasn't until we tried to measure the upper critical field in our 20 Tesla magnet, and we couldn't, we ran out of steam, and we couldn't break the superconductor. That's when I got really excited about it, and that's really when things started off. So the material itself is orthorhombic. So and it's not just a sort of stretch tetragonal; it's sort of intrinsically orthorhombic. So it has breaks that symmetry inherently. There's several ways to grow it. I'll flash that in the next slide. But from the beginning, basically, we kind of grouped it in this family of uranium superconductors that are well known. They've been studied for many years, and they're all known to be at or near ferromagnetism, and that's what makes them interesting and most likely spin triplet. UTE2 to this day, at ambient conditions at least, there's no long-range ordered magnetic state known. So that's why we placed it sort of at the incipient critical point of this family, within also inherently the highest TC of these materials. So what makes the material kind of both interesting and I don't want to say messy, but a little bit complicated is that there's sort of a width of formation of this compound. If you look, just temperature and well, some measure of uranium composition, but there's a width of formation. And so even if in the same furnace, as you just tune the temperature a little bit, you get slightly different properties, it seems. And that most people believe that's to do with some percentage of vacancies of uranium that are changing a little bit somehow. Although it's very subtle, it's like less than 1%, and it's very hard to actually measure. In fact, there's no, as far as I know, there's no really well-determined measurement of some systematic trend of this effect. Nevertheless, there's an effect on the TC and on the resistivity and so on, and some of the properties. Different ways to grow it. You can see this video journal of 2 ways to do it, and more recently, there's been different flux methods developed to grow higher TC crystals. And the nice thing is that all the groups more or less systematically yield the same quality of crystals. It's just dependent on how you grow it, what temperature, and so on. And so there's some good systematics in the field that at least we can agree on the properties more or less, and then we can compare notes a little bit more easily, which is not the case in many other materials. Just to compare to the other uranium superconductors, these are orthorhombic as well, but they're different crystal structure. I like to just point out that these compounds seem to have a sort of slightly zigzag uranium chain in the structure, whereas UTE2 has a linear chain that runs along the A axis. And in fact, it's sort of a ladder structure. So the shortest distance is actually between these two uranium atoms as you run along the A axis here. And then the tellurium chain, the tellurium atoms, there's two sites, but one of them has a chain going in the other direction here. And that's important for the band structure because both of those quasi 1D features result in quasi 1D Fermi surface.
So the ones on the left don't superconduct?
The ones on the left, uranium, rhodium, and cobalt, yes, they do. But they first go ferromagnetic. Yeah. So ferromagnetism, a few Kelvin, and then TC below about half a Kelvin. Okay. UT2 is well known for a long time as a condo heavy fermion type material, kind of sort of long forgotten. At least not the superconductivity wasn't known, but the sort of condo type behavior was known maybe 20 years ago. And the magnetization is anisotropic and it shows linear magnetization that has an easy axis along the A and hard axis along the B. And that seems to be reflected in the upper critical field anisotropy as well. The band structure, as I said, is comprised primarily of these quasi 1D sheets. And I'll note that as seen in ARPES, for instance, here, you can see these quasi 1D features. And these are D and P states, actually. So it's an open question where the F states are. That's an unsolved problem. There are some sightings. For instance, Andrew Ray's work saw this so-called Z pocket, which seems to have some heavy weight and likely associated with some F state. And I'll show in a second the quantum oscillations work, which there's been some controversy as to whether this has been observed or not. So the other thing to note is that you have to turn on U to get a Fermi surface at all. But so you get U of around 2 or so, 2 eV, and you get this this Fermi surface, this quasi 1D, these 1D sheets that hybridize to give you these sort of cylindrical-like features. Quantum oscillations were observed in the sort of newer generation of crystals about a year ago to start, and there's been several reports now of improving quality. Basically, the angle dependence of the oscillation seems to confirm this Fermi surface. So it's interesting because that was seen in photo emission. In photo emission, the dispersions are quite light. There are these P and D orbital-based bands. But here you can see that the effective mass is heavy, right? So it's up to upwards of 50, 60 masses. And that's measured directly through the amplitude of the quantum oscillations. So these are, there's heavy states here. And the question is, again, if you start counting electrons, where are the F electrons? How do you incorporate that? Sheng Ren's group actually did some recent work on quantum oscillations showing some evidence of a three-dimensional small pocket that they claim may be consistent with this heavy F part. And so, but there's some dispute about this, and I'm not, I can talk to you later about it, but there's some observations of it. Some further evidence of a 3D component in this band structure was from some of our own work, just studying the conductivity and isotropy. So the A and B was originally published, as I showed you before, this condo-like behavior. What we found that was new is that the C-axis resistivity actually has this unusual peak structure and looks nothing like the A and B resistivities. And these are absolute units. It's about the same order as the B. So if it's definitely not a two-dimensional system, the C-axis conductivity is comparable to the B-axis conductivity. It turns out, in fact, if you look at the magnetoresistance comparing A and C-axis transport, for instance, this is in 14 Tesla field, you can see that there's features, there's a minimum around 10 Kelvin in both of those. And we interpreted that as evidence of a 3D component that's contributing conductivities in both directions that's being affected by the the scattering that's giving you a minimum here. And just to compare the the magnetization has some evidence of a feature around the same temperature. So we relate it to some kind of magnetic scattering affecting this 3D component. Okay. So there's been several neutron scattering studies. This is also controversial. I'm going to tell you all the controversy today. It's also controversial, particularly the inelastic scattering studies. Pencheng Dai's group has reported resonance, neutron resonance in the superconducting state, which is unusual because it's a purported triplet superconductor. And following some work on strontium ruthenate, which has a related story, it was deemed okay, it's possible to have a neutron resonance at some Q vector, even though you have a triplet superconductor. Nevertheless, it's a bit unusual. And then our own work is a bit, has a story somewhat different than this in that we see a continuous dispersion as you cool down the system, actually going this way from 60 Kelvin down at this Q vector that suggests it's not just a antiferromagnetic Q vector or a spin fluctuation involved, but it's actually to do with some band transitions that are being seen by the neutrons. So all the data is consistent, meaning that there's some intensity along the baryon zone edge, along the B axis in all these studies. It's just, in a sense, the interpretation of the inelastic scattering that's a bit different.
Question. What is Q vector? Is it something vector that connects parallel pieces of the Fermi surface?
Yeah, but it's an incommensurate Q vector. So it's along the baryon zone edge.
So you have parallel pieces of the Fermi surface. Is the Q vector at which you see a resonance connects parallel pieces, or it's something different?
No, because it's incommensurate. So it's because of the orthorhombic baryon zone kind of stacks like this, as you go up along the C axis. So it's incommensurate because it's here and it doesn't connect the next baryon zone.
Okay. The question is about nesting.
Yeah. No, there isn't nesting.
But then you said that Q is connected to fermiology. In what sense is Q is connected to fermiology?
No, it's just that okay, it's a uranium story where the intensity along a certain Q vector may be related to interband transitions. Okay, because we don't know the band structure really well, it's hard to really explain that. But there's the similar story in uranium ruthenium 2 silicon too. Okay. Okay. Regarding the superconductivity, this is some of the original work we reported. There's a specific heat transition. Originally, we were extremely excited by this result because you see this heat capacity has a residual value that's about half of the normal state. And in fact, the draft paper we submitted was called half-gapped superconductor like helium-3. But it turns out, luckily we measured some thermal transport very quickly and saw that there's no residual quasi-particle conducting states, so we ruled that out. And since then, newer generations of crystals have had TC go up, and this residual term has gone down. So this is still unknown exactly, but it's probably to do with some kind of magnetic entropy that's lying around in the lower TC crystals. We also reported night shift that just sort of went through TC without any change. And that was the sort of first evidence of a triplet state. The other evidence was the extremely high upper critical field that just goes way beyond the polyparamagnetic limit. And in particular, this B-axis HC2 that just goes off scale, and that's the 20 Tesla that we ran up against in our labs and then had to go to the mag lab to subsequently measure what happens above that. So
does it turn, is there understanding why there is a sharp turn? Right.
Here?
Yeah, right.
Yeah, so this was followed up very quickly by our friends in Grenoble. And you can see that, so this is our data that I just showed. And they showed that They reproduce this, of course, to higher fields, and you see that it goes all the way up here until you hit some cutoff, which is believed to be a field polarized magnetic phase, first order cutoff of superconductivity. And then it's also very dependent on the angle of the magnetic field. So you can see that as you tilt the angle away from the B axis, this reentrant behavior actually gets suppressed. Okay, so that was the first indication of some reentrant phase, meaning, you start here and you go to superconductor, normal superconductor, and suggesting that there's two distinct superconducting phases here. So there's since been some heat capacity studies showing that there actually is some evidence of a transition here, as well as something between these two as well. But it's a subtle thing. There's some evidence of a transition, but I'd say because of the magnetic field range, it's a bit hard to really do the experiments you really want to do through that range. But we're trying to get at that. Okay. There's been about 10 NMR papers since our original work. The most recent on the highest TC samples suggest quote unquote large reduction in the night shift, which is actually just about 4 or 5%. Well, measured a 2% change. But the point that Aoki and company make is that there's a drop in the night shift in all three directions of magnetic field at TC, and that they conclude that this might be consistent with an AU symmetry, at least some component of AU symmetry in the order parameter. Okay, so as I said, early on, we measured thermal transport to try to see if we saw residual quasi-particle states. And we concluded right away that basically there's, in zero magnetic field, zero temperature, there's zero fermionic term in the thermal transport, which suggests that there's no residual quasi-particle states and thus not a half-gapped superconductor. But if you increase magnetic field, or for that matter, temperature, there's a very fast rise, which is consistent with a nodal quasi-particle excitation. And we interpreted that as a point node structure, where this is the magnetic field dependence at zero temperature, which rises quite rapidly, similar to uranium platinum 3, which is also a known nodal superconductor. Okay, so that's our first generation of measurements. And then just on Friday, we also just posted our newest work, which studied the same experiment, but in 4 different types of samples up to the highest TC samples. Long story short, it's the same picture. We see a very rapid rise at very low fields of the thermal transport in the zero temperature limit, which is consistent with nodal quasi-particle excitations. You can look at, or you can talk to me later, or look at this paper for some more information. For instance, there's some very unusual peak structure in the highest TC samples here, which we're trying to understand. Okay. All right, so I'm going to get to this in a second, but one of the conundrums in this field is in understanding the penetration depth data, which we reported along with our thermal transport data to show a nice quadratic rise with temperature, which is consistent with a point node gap structure. The unusual thing is that there's a quadratic temperature dependence in all directions of magnetic field. And that includes for different generations of samples up to the highest TC samples, most recent ones. So it's all consistent, similar to the thermal transport. And that you would use to conclude that there's some contribution of the nodal excitations in all crystallographic directions. And that's what pushed Shibayuchi's group to conclude that there's likely a 2-component order parameter where you have some splitting of the nodes off axis. And so at least there's some contribution from these excitations in all directions, as opposed to a single component order parameter like this. So that's at odds with some of the most recent experiments. So before I get to that, I'm going to just give you a quick review of the high field and high pressure work, because just when you thought the story was complicated, it gets more interesting when you apply field or pressure. So this was reported a few years ago. This I've talked about this B-axis magnetic field superconducting phase where there's two distinct phases before it hits this cutoff. If you tilt the magnetic field away from the B-axis to about 30 degrees or so, you induce a normal state above HC2, but then you re-enter this superconducting state above 40 Tesla. So that was a really exciting result. This re-entrant superconductivity way up in these pulse field regime, also inside this polarized phase. So more recently, and this also just appeared, I think, on Friday. So you can look at this, and there's an invited talk about this at the March meeting. So this so-called Lazarus phase actually extends if you tilt the field, away from the BC plane. It forms this sort of three-dimensional structure with pieces that kind of it's hard to see here, but they kind of pinch off. So there's sort of like let me go back one here. So this kind of parabolic shape, as you tilt away from this plane, there's a impeding another cutout here, and it evolves into sort of two distinct pieces and goes up in field as you go along. So I invite you to look at that paper, because even just understanding the fact that this upper cutoff sort of has a maximum and turns back down, even just from free energy arguments, is sort of at odds with a single component order parameter. So there's some, just from this shape alone, that it's suggestive that there's a two component order parameter up here.
And FP is the fully polarized, or
I'm sorry?
So the pink phase is FP. What is that?
Field polarized, yeah.
So isn't it weird that there's just a continuous line going from field polarized to the
Yeah, definitely. So so this line is defined by a jump in the magnetization. This jumps up first order transition, and here it's to some normal state, but when you get here, it's to some superconducting state. So for instance, I don't have it here, but you can see this is a jump in resistance, and then when you get to this phase here, it actually drops superconducting.
So the volume fraction is like 100% superconductor?
Yeah, as best as we can tell. So there's been some magnetostriction measurements from Los Alamos where they interpret it's consistent with a superconducting phase. Yes, but it's hard to measure in pulse fields. One other thing to note, this was Nick's postdoc Corey that did this work. I mentioned you can tune the properties of the uranium telluride by changing the knob on the furnace. You can turn it far enough to even make samples that are not superconducting at all, and that's how we think this was not discovered. In fact, the first studies of this material were not showing non-superconducting properties. So they took one of these samples and went to the mag lab and found that, so it's not even superconducting at zero field, but you can still induce this high field phase in these crystals that are not even superconducting, just in the cryostat without any field. So that's quite interesting, that this field survives even though the ambient condition superconductivity is nominally destroyed by pair breaking, although we don't know exactly what the mechanism is.
So,
yeah.
Right. What's the difference between blue color and red color, apart from superconductivity?
Here?
Yes. Two different phases in the magnetic field.
This is color coded by resistance. So dark is zero and red is high resistance. So this is some value of resistance. It goes up over here, but it goes to zero here.
So when you say FP, I assume it field polarized phase.
FP is field polarized.
So what's the difference then? You apply a field, and then there is what? There is a metamagnetic transition, or?
Yeah. Yes.
And the superconductivity is close to the boundary of this metamagnetic transition.
Yeah.
Thank you.
Yeah. Okay. Other questions? Going the wrong way. Okay, so pressure is another axis. What's amazing about this material is that all these phases happen within, the regime of measurable experiments, albeit at pulse fields and so on, but that also includes pressure. We can do all these experiments within the sort of clamp cell, pressure regime that you can measure in a sort of standard setup. And so it was reported a few years ago, in fact, that when you apply pressure, this is just a zero magnetic field, this transition actually splits into two transitions and it goes up to about 3 Kelvin. And if you follow the heat capacity, there's a lower transition that happens. So there's a two transition or two superconducting phase phenomena under applied pressures. And in fact, if you sit somewhere here, about 1 GPa in applied magnetic field, that's what this is. There's up to 4 superconducting phases distinguished by some kind of specific heat transitions. Okay, so there's a lot of debate right now about what the ambient pressure zero field superconducting phase is, whether it's single component or two component. I'll show you evidence that we think it's single component now. But clearly, when you apply pressure, there's multiple competing superconducting phases. It's very rich. And now when you take this up to high fields, that's an even more complicated phase, and I'll show you in the next slide. Okay. So that's this. So the previous high field phase diagram, when you tilt the angle of the field is this one. And this is this reentrant phase. So now if you sit at this quote unquote magic angle, it's not a twisted bilayer or anything, but if you sit here and now apply pressure, it turns out you can reduce this transition down and increase this low field phase up until they meet. So in fact, there's continuous superconductivity up to at least 45 Tesla at some pressure around 1 GPa. But it's clear that these are two distinct phases. They kind of run into each other. And we're working on trying to do some, this is just transport and TDO experiment. We're trying to do some other measurements, for instance, tunneling, to see what the distinction is between these phases. Okay, and then there's some more rich behavior here, which I'd be happy to talk to you about afterwards. Okay, so early on, I mentioned that the consensus is gearing towards a single component order parameter at ambient conditions in UTE2. The first reports actually that we produced were suggesting that it was a multi-component order parameter. And that's because there was indication of two distinct superconducting transitions, zero magnetic field, zero pressure. And from the work of Kapitolnik, time reversal braking due to onset of a Kerr rotation at TC, spontaneous. Okay, so from that work, we concluded that there was a likely, B3U plus IB2U or AU phase in this ambient condition material. Now, more recently, with slightly higher TC samples, it's been shown that, oops, not been here. Oh, I lost it. Okay. Sorry, I lost the slide. It's been shown that the higher TC samples don't show any evidence of this two superconducting jump, just a single transition. And so we've been studying this with similar probes to see what happens there. But at least at this point, there was this, sort of consistent picture of time reversal braking, two TCs, quadratic temperature dependence in two different directions, suggesting multi-component order parameter. Yes?
Sorry to interrupt, but if you have two component order parameters from A plus IB, you normally don't have any nodal quasi-particles.
You can in 3D.
Sorry?
You can in 3D.
In 3D,
You can,
yeah,
right?
in 3D, yeah.
Okay, sorry.
It would be a vial.
Yeah, sure.
Yeah, and to remind you, it's orthorhombic symmetry, so you have to have two components to explain like these properties, including time reversal break, evidence of time reversal braking. Okay, so this is still controversial. I'm going to skip that. Because more recently, the Los Alamos group has done Kerr rotation experiments, and now they're suggesting that there's no evidence of time reversal breaking, at least within the resolution of what was reported previously. I'll leave that at that. These are two different groups that measure two different things. I have some thoughts on it, but there's some consistency, at least, that when you apply some magnetic field, and this is an interesting experiment, you apply a magnetic field and then you turn the field off and then warm up and measure the Kerr rotation. So it's like, plus 500 Oersteds, field cool, turn off the field and measure in zero field. And there's a Kerr rotation that exists there. And it's thought to be due to the vortex response. So Aaron's group has suggested this is evidence of some magnetism in the vortex cores. And it scales with the magnetic field you apply, some trapped flux. So that's at least consistent. But the zero field cooled spontaneous Kerr rotation is under debate. Okay. Oh, here it is. I'm sorry. So the higher TC samples show a single transition, and that's been shown by every group, including ourselves. When you make the crystals in that way, you have a single transition. So that's a slight difference, yes. Now, there was some evidence from STM early on from Vidya Madhavan's group that on the surface, at the very least, there's some chiral state that's consistent with a, there's some response that's consistent with a chiral superconducting state on the surface. And she saw this when you run up against a step edge, she saw this asymmetric response in DIDV that is reflected, mirror reflected when you go on the opposite step edge going down. You see the mirror symmetry here, meaning that there's some chirality to this state that's along the edge. And so this was also interpreted in terms of a chiral superconducting state. Okay. And then finally, my colleague at Maryland, Steve Onlaga, measuring microwave impedance measurements, found evidence of a huge contribution to the conductivity in the superconducting state that, together with our bulk thermodynamic measurements, suggested that there was a very large normal state surface response. And so, this was all consistent with this chiral surface state that was there. Okay. So I keep going, gets more complicated. This is certain, the surface is always, what's the claim, the note, the quote, the surface is the work of the devil. Is that how it goes? Okay. So in this case, the both Vidya's group, Seamus David, and also Ilya Yelkovich have all observed charge and pair density wave states on the surface. It's not clear whether this is in the bulk or not, but I think consensus so far is that it's only surface. There's no evidence of a bulk charge density wave state in UTE2. Nevertheless, there's some incommensurate charge density wave states, and also in the superconducting state, it's been interpreted as pair density wave in the superconducting state by both groups with slightly different interpretations. Okay, so that complicates sort of the surface response, as some of us know. Okay, so back to basics. What's, so if there's a bulk gap symmetry that has nodes, following Liang's work, he's not here anymore, so I can say whatever I want. Following the sort of analogy of the vial semi-metal case where the vial nodes project and give you some surface arcs. There's a similar story in the superconducting state where you can have Majorana arcs on the surface and have these surface states exist. You have this kind of order parameter. So that's kind of what we've been trying to investigate. Most recent work with Brad Ramshaw's group doing ultrasound, we worked very closely with them to try to nail down the bulk gap structure, symmetry, in fact. And so there's a nice table in Florian's paper, and he's going to give a talk in the invited session, I think tomorrow. Looking at all the evidence for different order parameter symmetries, including one component and two component from all the different experiments. And asking the question whether you would expect a discontinuous jump in the shear elastic constants from ultrasound. And so, it's very clear that in the two component cases, you need you should see a jump in the shear elastic constants. If it's a single component, you shouldn't. That's nicely summarized in this schematic here. Basically, when you have this asymmetric order parameter, when you apply a shear strain, you expect a jump in the shear constants like this. And if it's a single component order parameter, you don't. You can see a kink, but not a jump. This is just thermodynamic constraints. And so here's the data. And the important thing here is that we studied both a single TC sample and a double TC sample. And it's hard to see, but you can see this little kink here. That's a sample with 2 bulk superconducting transitions as measured by specific heat. And you can see it in the ultrasound. So this is the compressive C33 constant. You can see the jump very clearly and 2 jumps in this one sample. But when you look at the shear constants, there's no jumps. There's kinks, but there's no jumps. So in essence, this is evidence for a single component order parameter. Unless the amplitude is so small that it, and the only caveat I'll say is that there's something unusual happening in C44 where we don't see anything. Okay. And so that might be a way out, but at least the conservative conclusion is that it's a single component order parameter. So beyond that, I'll just need one more, just 30 seconds. Beyond that, given this lack of response along C44, Brad argued that this is evidence that the nodes in the single component order parameter are actually along the y direction. So that would be consistent with a B2U symmetry. Okay. So I think this is my last slide. So dare I say the M word? Okay. So I showed you that there's evidence of definitely nodal excitations in this system, bulk nodal excitations from thermal transport. There's some evidence of a chiral state, at least on the surface from STM. And there's definitely a normal fluid response on the surface from microwave impedance measurements. So what's going on? Well, we're working on this. The most recent results, and I'm showing this even though I probably shouldn't, is from Seamus's group, where they did a superconducting niobium tip tunneling experiment. And so this is the niobium gap here. But within the gap, you can see a nice peak at zero bias, which Donghai Li is interpreted as evidence of a surface Andreev bound state. And we also should appear tomorrow. We've done some point contact experiments, also showing some zero bias peak that's consistent with the Andreev bound state in the system. So, room full of theorists, I ask you, what's the story here? At the very least, there's some interesting surface states on this material. That's a definite statement. Okay, so to end, I hope I gave you a sort of overview of what's going on and some recent results, at least in our work. And I invite you to come to some of the invited sessions tomorrow and Tuesday to see some more updates on what's going on in the field. And that's enough. Thank you very much.
So my question would be this. So imagine that you're in SC1 phase. So is there a time reversal symmetry breaking or not? And how to reconcile the time reversal symmetry breaking with a single component order parameter if there is this breaking?
Yeah. Well, I mean, there could be a concomitant magnetic phase or something that hasn't been detected. That's possible. I'll just think of ways out of how you would have time reversal breaking and a single component order parameter in the bulk. As I said, the earlier generation samples seem to have some kind of magnetic entropy at very low temperatures that you can see in heat capacity. One thought is that there's some crystalline defects or some kind of substructure that is no one's observed yet. We're just speculating, that give you some kind of magnetic component that's there. And maybe it facilitates some magnetic order that's there. It's hard to see. There's been no observation of magnetic order. So I'm just saying, if there's time reversal braking, there could be some kind of magnetic order. Maybe it's short range or something. I'll just say something about the Kerr effect measurements. One group is arguing against the other. You can say, for instance, that there's this effect of domains when you cool down the sample, the spontaneous domain formation. If your spot size is bigger than the domains, then you could be averaging out the observation. That's one argument. The other is just there's just no time reversal braking. So
as far as I understand, the thesis would be that you've got Majorana Fermi arcs coming from these nodes from above, right? But the gap is likely very small, right? So these Majorana arcs are basically a card of superconductivity. Right? So does this material have any other surface states? For example, in the normal state, can I think of what's happening on the surface might be just surface superconductivity, and you get some stuff out of. Do we know about the normal state, surface state?
right.
Because it probably has a lot of them.
We have some interesting data I can't share yet. But
why not? We're private.
well, if I had evidence of surface states in the normal state, I would tell you, but it's hard to interpret. We can talk about it after.
Okay.
One other possibility I'll suggest is that, as I showed you, magnetic field, pressure, this system is very sensitive, and there's obviously multiple superconducting states. I mean, 1 GPa of pressure is nothing, right? So you could imagine that at the surface of this material, you have some stabilized state that's different than the bulk. Another alternative than just a state generated from the bulk gap structure.
What about mu-r measurements of broken time reversal symmetry, which don't require this sort of elaborate field time training? You wouldn't have these vortices.
So
I also want to ask on the samples which show this double heat capacity peak. Normally, if you had just an inhomogeneous sample, you'd expect to see a broad peak. The fact that you see sort of reasonably sharp features implies that there's kind of two phases there.
Right. So that's why I'm not dismissing our own work yet. We did a lot of work to rule out that it's just some, two pieces of crystal stuck together with slightly different TC. It's very clear that there's two distinct transitions, and you're right. If there's a, disorder effect, there'd be a broad distribution of TCs, it'd smear out or something. But there's clearly, two distinct transitions as shown in the ultrasound, for instance. But we can't rule out that there's just some, sort of microscopic stacking fault or something that gives you two distinct phases. It hasn't been observed, but you could argue that way too. Regarding mu-SR, Jeff Saulnier's most recent work suggests that there's no time reversal braking. They've studied the highest TC sample, and they don't see anything going through. So their latest measurement suggests that the magnetic fluctuations are reduced in these higher TC samples, and they have the resolution to be able to see time reversal braking, and they don't see it. But there's been an evolution of mu-SR data, which I would still like to understand before I think just close the book on that, which we can talk about.
Maybe this is a question for your theorist co-authors, but wouldn't it be a bit strange if you had two distinct EREPs with the same TC, or is there some reason?
Yes, it would be strange. Yeah.
Do people have any suggestions for what?
Meaning, if you had a multi-component,
yeah, if it's like
with the same TC that was degenerate, yeah, that would be strange.
In a more simple way, your best samples, highest TC. If you look at specific heat, two questions: from the jump of specific heat, the extended analysis, is it strong coupling or BCS? Question.
Yeah.
And second, can you, for your best samples, extract from low temperature dependence at least whether it's power law or exponent?
So
like power law.
Here's a good example.
Yeah, perfect. So
definitely power law looks like T cubed.
Mm-hmm.
Really nice T cubed. And interestingly, T cubed all the way up to TC, which is strange.
And what's
The jump, I'd say the jump seems to vary with sample. So I don't think that's understood yet.
No, but I mean the standard delta C over CTC.
Yeah, it's
Standard
a
beta,
little
standard.
larger than BCS. But the gap seen spectroscopically is about BCS, roughly speaking.
Sorry, one question. Is the photon spectrum known in this or?
Is the phonon spectrum?
No.
No.
Okay, no question, please.
Thank you.